Lingkod na po dito. Sorry. Gusto na? Ano ba? Gusto na? Ano ko din? Ito na?
Upang yan.
Ano nga na bang
Good morning. I am Srihar Rao, and you have been seeing me here and there moving. Okay, so generally I keep moving here and there, and then I speak a little bit whatever I know. So thanks to the main coordinator, Mr. Muralidhar Garu, for giving me the opportunity to speak to you. And yes, I would like to have a brief idea of what exactly the background. That of course I have attended some of the couple of lectures, of course. So my intention is to just cover the basic building blocks right from the characteristics till the differential amplifier. But I just want to know anything is already there, covered or no, then I'll try to move fast. You just let me know, right? So that's what is the idea. I understand that there are people from mechanical as well, therefore it helps proper bridging. But then I may move a little bit fast because keeping in view that so you are aware of things, right? So therefore let's try to so noise is a big problem in the analog IC design. So to just see that how noise impacts, probably noise is being who are actually dwelling with the analog design, right? So there are some of the circuits which you are already designed and all, but then let's try to just look at what are the intricacies of analog IC design. Why at all you are going for analog IC design is well known, right? So what is the reason why you are going for analog IC design? Pardon? Calculating analog values and removing the noise. How about you? Can you please come into line of sight? Anyone else? Anyone else? Why you want to go for the analog IC? The analog IC design in this sense, basically the circuit, whatever the design you are actually doing, these circuits are supposed to take the signal in the analog form. That's all. So we would like to process the signal in the analog form, right? So we all are well aware that as the technology is being scaled down and all, we are able to make use of the computational efficiency, right, which is in the art of terabits per second or whatever it is. Therefore, we would like to allow the signal to be in the digital domain so that the processing is very efficient by virtue of the different several reasons, right? So what you can exploit the computational efficiency of the computer, and then what else you can do? Probably the coding is very easy, and then right. So basically security you can bring in, and very more important is noise immunity, right? So in the case of digital processing or digital representation signal, you have got very good noise immunity. Noise immunity in the sense, after all that required is you have to just transmit either 1 or 0 or maybe finite levels. Therefore, a lot of noise immunity is there, and security is there, right? So because the various state of the art algorithms you can apply, and lot many advantages, right? And you can store the data in a very compact form. So therefore, obviously for all these reasons we want everything to be digital. So it's not an exaggeration to say that I keep on just telling the later no that the whatever the beauty parlors, gents beauty parlor, I'm just speaking that the digital barber shop, right? So therefore you try to just put the 10 10 10 just right? So people are very crazy about that, and that is justified. But still, then you may say that you old man, that you're sticking away. Still, you are sticking to this analog. Seems to be very not required. It's not probably that appears to be right. And also, probably if we had to look at the complete system, in the complete system, more than 80%, almost 80% is digital subsystems only. Only the analog subsystems occupy 20% or whatever. So then why should we actually spend our valuable time and then towards that very small portion of the digital analog which is there in the entire, which is occupying the entire system, right? So, the fundamental question here is, first of all, can we dispense, can we just throw it out, total digital thing only, why if it is not required, question. So, the answer probably is digital itself is nonlinear, let me tell you, right. So, probably I will try to put it in the other way around. Whatever I am speaking, for example, but actually the signal that we are going to ultimately, what is the purpose? So, we try to get some signal and try to do some processing and then convey it back, right. This is what is ultimately any system does, whichever is the nature of the signal, whatever is the nature of the signal, whatever the type of the signal, right. So, for example, I am speaking this speech signal, right, which is basically what kind of signal it is? It is a mechanical signal. What I am doing here is just know by while I am speaking, the air is being compressed and rarefied. So, there is compression rarefactions. So, then the diaphragm here of the microphone is going to just know, it is moving, then therefore carbon granules are getting compressed or factor, right. Therefore, accordingly the resistance, when you are going to apply voltage, then resistance is going to vary, and therefore current is going to vary, and ultimately it is converted into the electrical signal. Therefore, this mechanical signal is being converted into the electrical signal. And then if you try to look into the if you try to see, you want to see how the waveform looks like in the CRO, it is a continuous waveform, right. It is continuous in the sense that it is continuous with respect to time as well as continuous with respect to amplitude. So, therefore, it is that is what is analog signal, right. So, if you ask me to, hey, come on, I want a digital signal, come on, you just produce digital signal, I can't, right. So, therefore, not only me, indeed also you, right. So, however fascinated you are about the digital signal, right, not only that, and if you try to look at the kind of signal, not only speech, the kind of signal that is being generated from in the physical, in the world, then in the real world, majority, 99% signals are analog in nature. They are analog in nature, right. Therefore, immediately that brings in attention that, oh, the original signal is analog in nature. So, then you may say that, all right, somehow I will extract whatever, I will try to make use of transducer like this, and then it will convert into the form, the electrical form, and then what I will do immediately, I will jump start, and because I want to go for digitization, because nowadays what is happening, nowadays all sorts of branch of engineering are removed, and just AI and ML only, right. So, just jump start, and then you want just to go for digitization. When you go for digitization, can I do that is the question here, that can I do immediately go for digitization right after the activation of the signal, right. So, if you try to do that, what will happen? If you try to do that, what will happen? The kind of the signal is being extracted from the nature, I said it is analog, not only the analog, it is also very feeble in nature, very small in amplitude, very small in amplitude, surrounded by a lot of noise, as just now we have experienced, right. So, a lot of noise is that, because by the virtue of the beautiful speaker and fidelity you are able to listen back, otherwise it is actually surrounded by noise. So, the noise is going to dominate, right. And now if you try to use what about, if you want to convert the analog signal into the digital, what you have to do? You have to apply, you have to use analog to digital converter. When you try to use analog to digital converter, what will happen is, already the signal is surrounded by noise, and it is very feeble in amplitude, and now you are quantizing it, and therefore what will happen is, these samples are going to die down in the presence of this quantization noise, right. So, therefore you will not be able to recognize properly, or otherwise I can say that the majority of the samples are just dancing within one level only, or so, right. Therefore, which implies that basically it is a suicidal attempt to just go for ADC right immediately after the signal acquisition. Therefore, that over and above, I am just not telling not only quantization noise, it is surrounded by the other noise also. Therefore, there is no way that you will have the intelligible signal at the output, quality signal at the output, right. So, what you are going to quantize probably is noise, right. And therefore, what you have to do is, the signal thus acquired from the various surrounding whatever the physical available source, what you have to do now? You have to first make it clean. You have to make it first clean and make it healthier, stronger enough to be digitized, right. So, that is what is signal conditioning. What you will do probably, you have to use a filter, amplification, and whatever the processing you have to do. So, for all these, the filter is a circuit, right, and the amplifier is a circuit, and any other signal conditioning circuits are there. So, all these circuits, what is the signal that they are going to take? which form it is? Analog. The signal in its innate form, this analog form, is being applied. That means the circuits which you have to design have to deal with analog signal, there is no alternate. And the challenge is the signal is very, very small and there is a lot of noise is there, and therefore you have to give a beautiful amplified analog signal which is having very good signal to noise ratio at the output, so that you will be able to digitize it in a proper fashion, right. So then you may say, all right, there are people, they will do it, otherwise it is not my cup of tea, it is not. What is the challenge there? That is the question. So it is no big deal, amplifier, filter, so there, बच्चे लोग करते हैं, this is very, very, very small. When people do that, when I am just going to do something else, then let's say just see, is it that simple, so that now you can leave it to the winds or someone, whatever it is, right. So the problem, the kind of the problem, if you look at, you know that the technology as it is being scaled down, the technology, you are well aware what a technology is, right. What a technology is, what do you mean by technology? In the context of the IC design. In the context of the IC design, what is technology? Pardon? What do you mean by technology? What do you mean by technology? No, you have been using here 180 nanometers technology, you are telling, right. So otherwise 130 nanometer technology, otherwise 45 nanometer technology, or otherwise probably you will go even for what is the state of the art, say the 5 nanometer technology, right, even less than that, right. What it refers to? It's not space, it is. So it is the generally vaguely speaking channel length we say, right, vaguely speaking channel length, right, channel length we say, right. So the channel of the transistor MOSFET, right, or to be precise, it is the resolving capability of the delineating equipment of the photolithography which is used in the IC fabrication, right. So resolving capability of the delineating equipment which is used in the IC fabrication. What is this resolving capability of the delineating equipment of the lithography which is in IC fabrication? So speaking very simply, I think you can just recall that for the IC fabrication and all, what you do is you prepare masks and all, right. So you know that MOSFET, you just recall, we are going to see that as we progress, but then for the time being just to recall whatever you know, the MOSFET has got the source, drain, gate, all this, right. So there is the silicon substrate is there. On the top of that, actually we keep on doing some sort of processing. What we'll do some sort of a diffusion, some sort of ion implantation, all these things we'll do, and certain areas we just expose, certain areas we mask. How do you do that? So probably you can just think of creating a mask. There is a silicon substrate is there. Create a mask. What the mask does, I said, no. Suppose you want to create the source and drain, right. So on the substrate, you just expose the source and drain selected areas to diffusion, and other area you don't want, you mask it. So that it's just like in your Bombay dyeing, whatever it is, you have got various designs, right. So the design is there on the top of that, if you just put that color and then it gets printed, right. So therefore here also you try to expose some areas and there the diffusion takes place, right. So therefore n plus you are able to get some pockets are there. It's just like take a paper. Generally I ask the students to take a paper and to create two perforations, two rectangles, draw 2 rectangles, do perforations, and then right. So while doing so, if you have any paper, generally I think this only gives, this is the only way that you can understand in a better fashion. I'll just now show it. So assume that notes ఇచ్చేయండి, notes మొత్తం ఇచ్చేయండి, notes మొత్తం ఉందే, okay, right, it is there already. Just keep it like this. So already what I have done here, see, this is the I have taken a mask here. So then I have just now drawn with a pen two squares or whatever, and create, then just remove this. Therefore, this is a mask now. This is the p-type silicon substrate. On the top of this, I am just trying to keep, and I am trying to do some sort of a diffusion, right. So, n plus diffusion, then what it does, only on the selected area you are able to do that, right. So, these two are separated, right. Now, this is a, if this is the case, I have used a pen and have done it, right. Suppose if I use where is that, a marker, okay, just give me a marker. If I use a marker, one minute, mighty call ICT Academy, but then we are going to use C2S tools. So, for it, therefore, we try to use instead of this one, if I use a thick pen like this, and I want a separation of, suppose let us say 2 centimeters, I am able to get it. So, if I try to get a separation of 1 millimeter or 0.5 millimeter or 0.05 millimeter, then if I try to use the same thick pen here, right. So, right. So, as the separation keeps on as the separation narrows down, what will happen as separation narrows down, then this thickness will be a bottleneck. Am I right or not? Right. So, therefore, this is what is the resolving capability of the delineating equipment, right, for the lithography. So, I want to have a separation of what, 180 nanometers or even, right, 5 nanometers, then this does not help because they will overlap, right. Such a small separation not possible. But then, so the lithographic equipment, this is what is the delineating equipment. Therefore, lithography, the improvements in the technology are allowing to have such a finer resolution lithographic equipment which can prepare such masks, so that they will not otherwise if the source and drain they just not join each other, there is no physics at all. The kahani nahi hai, right, there itself will be over, right. So, there should be separation, right. So, this is what is technology, is it okay? Now, coming back, so as the technology is being scaled down, what is the challenge here, right. So, as technology being scaled down, more and more devices are being shrunk and they are able to, they are kept in a smaller area, all right. So, but now what happens is, what happens to power supply? What happens to the power supply? The power supply which you are going to use, for example, for 2 micron technology, the power supply is suppose 5 volts, right, and for 180 nanometers, the power supply is 1.8 volts, and for 130 nanometers or even below that, we are going for 1 volt or even sub 1 volt, right. This is the supply voltage also we are bringing it down. Why can't I use the same power supply which I have used the higher power supply 5 volts or whatever for the scale down technologies is the question. Can I use or not is the question. Can I use or not? If I use, then some problem is solved. Can I use? Why should I actually bother about this? Why I am bothering is, I will pose another question here. This is the circuit which you are going to build, right. So, in an amplifier you are just making. What is the maximum possible value of signal at the output of a, what is the maximum possible value of the signal at the output of an amplifier? For example, there is you are asked to design an amplifier. So, the amplifier, the signal is let us say 10 microvolts, right, or 100 microvolts the input, right, and then you are asked to design with a gain of let us say 50,000, right. So, what will be the output value? What is the output value? Signal amplitude is 100 microvolts, gain is 50,000, right. So you are doing that, you are taking the transistors, rigging, and then you are trying to see the output. What is the output in the lab? You are doing the lab, right. What will be the output? It is not a big, it is simple question, it is, right. Input signal amplitude is given to you, gain is given to you, amplifier gain. What is the output that you are going to anticipate? 100 micro into 50,000. 100 micro into 50,000. How much it is? 5 volts. Is it right? Is it okay? Everyone is, suppose it's a 1 millivolt, or let us say 10 millivolt is input. 10 millivolts and the gain is 50,000. What is the output? Ten millivolts, 50,000 is the gain. 50 volts. So you have done in the lab, right? So such an amplifier you have designed, and then did you ever see 50 volts at the output? We are electronics engineers, right? We're not dealing with electricals. Did you ever see in the lab 50 volts? Amplifier specification is, of course, 50,000 gain is possible, and I can also give 100 millivolts is also possible. I can give 100 millivolts as input, and 50,000 as the gain also is possible. I can design an amplifier with the 50,000 gain. 50,000 means in the decibels it will be, right, some 80, 90 dB or whatever it is, or even less than that, right? So it's possible, both are possible, you have designed. So, but are you able to get your so-called 50 volts at the output or not? Will you ever get? Why? What is gain you are telling? Signal you are given? You design the circuit? Then you suppose आपके बात तो मानना पड़ेगा. It has to listen to your instruction because you have designed for it, right? You should get. But you are telling you are not getting. Why? What was the reason? Pardon? Not required. Not required. Who said? Who said? How the amplifier works? How the amplifier works? How the amplifier works? Amplifier in any system, so you know that energy can either be created or be destroyed, right? So what it does, it takes energy from the power supply, DC power supply, and it translates into the signal power. Am I right? There are two things here. Signal is the one which you want to process, and VDD is the DC voltage, right? So it takes the power from the DC, and then it is going to translate it to the signal, and then you are going to, right? So therefore, what is the maximum value of the signal at the output of the amplifier that you can anticipate? What is the maximum value of the signal at the output of the amplifier that you can anticipate? Loud. VDD. So there is no other alternate, right? So for the circuit, there is no other source. It's not a Brahma that it will create anything, right? So therefore, the maximum value is only VDD, right? So maximum possible value of the signal at the output of the amplifier is VDD. Now keep that in mind. That's why I am now speaking about when the technology is being scaled down. When the technology is being scaled down, so what is the power supply is also being scaled down, I said, but then can't I use the same power supply? Why? Because I want to get a higher signal at the output. I want to have larger swing, right? So therefore I want to retain the same, right? Even if I scale down from 2 micron technology to 180 nanometers or even lower that, then I want to retain the 5 volts only, so that I am happy because my signal I will get larger output, right? Can I do that is the question. Can I do that is the question. Can I do that? Can I do that? Are you able to follow or not? So can I do that? Can I? Right? If it is done, then what will happen? So as the technology being scaled down, what is happening actually? More and more billions of the devices are being packed into very small area, more and more devices. Now what is it I am going to do? If I use the same 5 volts whatever, higher voltage, and the electric field intensity per unit area will be enormous, right? Therefore the device will break down and they will not work, right? Therefore what, because ultimately it is a field effect transistor, right? So there is no alternate but to scale down the supply voltage as the technology is being scaled down. as technology is being scaled down, you have no alternate but to scale down the supply voltage. So one way I said that signal value, maximum possible voltage signal is reduced, but then you are also happy that chalo I can use smaller voltage only. Suppose your portable devices, I will use a smaller battery on this, battery with smaller voltage only, I will use it, right. So that it appears to be blessing in disguise, right. Alright, so now the question here, what is the bottleneck here in the analog design, just would like to say, right. So the first point, the first observation is, as the technology is being scaled down, the maximum possible value of signal is coming down, right. The other point that we would like to see is the supply voltage is being scaled down, but then the threshold voltage is not getting scaled down at the same rate as of the supply voltage. The threshold voltage is not getting scaled down at the same rate as of the supply voltage, right. So threshold voltage, if there is 1 volt there, then in the same proportion it is not getting scaled down, right. So it may go down to only 0.7 volts, right. So or even little bit down, but not at the same proportion as the supply voltage. 5 volts to you are coming down almost to 1 volt or so whatever it is, but the threshold voltage is not coming down at the same rate. It just still remains at 0.4, 0.3, whatever it is, right. So now how does it matter for us? How does it matter for us? This question. Later on I will make a statement which I am going to justify it later on, but then just note, take it granted for the time being, if you do not know that, I need to maintain a voltage of VGS minus V threshold at the drain of the MOSFET, right, to keep it in saturation, right. So for whatever the reason, I will just see later on, I need to maintain a minimum value at the drain of the MOSFET, right. So because this threshold voltage is not getting scaled down, this minimum voltage which I am going to keep at the drain is not going down, is not going down. What is this voltage? This is DC value I am telling. The DC value which I have to maintain at the drain of the MOSFET, it is not going down at the same rate as that of the supply voltage. It is as good as, just imagine the, for example, I'm not a good dancer, but some of you probably who is very tall enough, handsome or beautiful, they can you can think someone is dancing here, right. So therefore, is dancing, then what is the room dancing to make an impact, what he has to jump so much, right. What is the room available here? From floor to roof, right, till this you keep on jumping, then you are very happy, you can see it. Now what happened? The roof has come down because the VDD has come down, right, and what is happening? The floor is not going down at the same rate, right. If this has come down by 2 feet and this floor is going by 2 inches, then think that what is going to happen? The room available for me to dance is reduced. Am I right or not? So will you be happy? So because dance is not that effective, right. So this is as good as signal excursion. For the signal to swing from maximum to minimum value, the available room for the signal swing is being shrunk, right. Is it okay? So signal maximum possible value of the signal swing is at stake, is being reduced when the technology is being scaled down with what? Analog signal, right. And what else? Maximum possible value signal is coming down, where the noise floor is remaining the same. The noise floor remains the same or even it increases because more number of transistors are being packed in the same space. Probably noise floor keeps on either increasing or remains same, whereas maximum possible signal is coming down. Therefore, signal to noise ratio is severely affected. It is coming down. Swing gaya, signal to noise ratio gaya, right? Both of them have gone, right? So, and there are many other challenges like channel length modulation, right? So there is a drain induced barrier lowering, right? Hard carrier effect. There are many other artifacts which are associated with the scaling down of the technologies. But then you have to live with the scaling down of the technologies, and then it's because the advantage you want to just go for higher speeds. The major advantage for the scaling down technology is you can operate at a higher and higher speeds, right? Because capacitors, associated parasitic capacitors are going to be smaller, and therefore the FT, which is unity gain frequency, is going to be pretty larger. Therefore, and indeed all these whatever the applications to nowadays, they demand what? Very tremendous data rate, right? Because all are connected, everything is connected together, and therefore you want to have a what you call seamless data transfer, and obviously you want to have a very high data rate, right? So that means your device should permit it. Your device should permit such a high frequency operation. So therefore, indicate frequency should be as large as possible, right? If you want to do that, then obviously you have to go for smaller technologies. Not only that, more and more functionality you want, therefore a lot of action should be packed in a smaller area, and obviously you have to go for scale down technologies, right? So all right, therefore the challenge here is I want to use the scale down technologies, but at the same time I have to live with all these challenges. What is that? Signal swing, signal to noise ratio is a problem. Then in spite of that, I should be able to design my circuit to meet the required specifications. That's what is the challenge. Therefore, it boils down to the fact that there are various trade-offs between the various parameters, right? Performance parameters. You can see that so over and above, any system is nonlinear, you are well aware, right? Any system is nonlinear. Basically, the other day I have seen that what is nonlinearity and all is introduced in a beautiful fashion. So therefore, what happens is by the virtue of nonlinearity, what will happen is, for example, a system is nonlinear. Then if you try to give a signal at the input of the system here, a signal, let us say some a cos omega naught t. A cos omega naught t is the signal that is given at the input. And this nonlinear system is how it is defined. It is just like now if xt is the input here, then some just like alpha xt plus some or alpha 1 xt plus alpha 2 x square t plus alpha 3 x cube t, like that. That is the characteristic of the system. Yt is equal to alpha 1 xt plus alpha 2 x square t plus alpha 3 x cube t, and so on will be there. These are the nonlinear terms. Had it been only alpha xt, if xt is the input, alpha xt is the output here, then it is a straight away linear system. But then these are this is not the case. In which case what will happen? You are given an input as xt is equal to a cos omega naught t. Then what will be the output here? It is a alpha a cos omega naught t plus alpha square, it is a square, no, x square t. So what will it will be? Is a x square in the sense it is a cos square omega naught t. Cos square omega naught t is 1 plus cos 2 omega naught t divided by 2. So what are you getting? Additionally, some DC is getting, you are getting, and then 2 omega naught t term also you are getting, which is not there in the input. And if you go for the third terms, that is the cube terms, then you will get the other frequency terms also, right? So not only that, that means the frequency components which are not there in the input are visible at the output. Not only that, if there are inputs will not be single tone, right? Input there can be multiple. A cos omega 1 t plus a cos omega or b cos omega 2 t and so on, whatever. Then what you will get here when it is squared, then you will try to get omega 2 minus omega 1 term, omega 2 omega 1 minus 2 omega 2 minus omega 1 term, like that you multiple components will get, right? So all these are third order terms also will be there, right? These are called third order terms. So when the frequency is very small, later on you are going to just to visualize, you can draw the spectrum. All these the additional not only harmonics means square terms, when cos square omega t 1 plus cos 2 omega naught, therefore omega 1 is one frequency, then 2 omega 1 or 3 omega 1, 4 omega 1, all these are harmonics. In addition to the harmonics, you will get all these third order terms. They are 2 omega 2 minus omega 1, right? That means when frequencies are very close to each other, then what happens? These harmonics are further closer to the desired frequency, and using a filter, you will not be able to get rid of them. That means they are going to be there in the pass band, and therefore it is very difficult for you to just filter out the undesired frequencies and only get the desired frequency, the output. Therefore, this is a big challenge, right? So therefore, the design of such a nonlinear system is really a challenge, okay, and therefore you can see that there is a lot of trade-off here between the power dissipation and power dissipation and input and output impedance, and then with the speed and the voltage swings, and then the supply voltage and voltage swings, and supply voltage and the gain, right, and then gain and the linearity, and here gain and the input output impedance. So the larger the output impedance, you will have the larger gain, and similarly I can also see that the voltage swings and the noise here. So the larger the noise, the voltage swing is going to be compromised, right? So therefore there is a lot of trade-off amongst the various performance parameters, right? Yet you have to design meeting the requirements. So how do you do that is the question. You cannot excel everywhere, right? Based on the requirement, based on the application's demand, you try to emphasize some application demands very good gain, some application demands larger bandwidth, right? So that means very high speed, whatever. So depending upon some application demand, very signal to noise ratio should be very large. For example, the very front end of RFIC receiver, the first stage is a low noise amplifier. There we don't bother about the signal gain, but then we bother the signal gain is only about 20 dB only. We don't just look at much signal gain, but then we only bother about noise performance there. So therefore we will emphasize that the noise is very much reduced, right? Because subsequently the noise whatever it is, it will be divided by the gain of the other cascade stage. There is a freeze formula, right? So therefore based on the application, we try to emphasize certain parameters and try to meet the trade-offs in a efficient fashion. How do you get it is basically you have to experience it. Therefore it is not right. You just cannot a single day, otherwise there is no systematic procedure, this and therefore you will get this. No, this is, you have to experience, you have to design it, you have to design experience. With that only you will be able to do it. Okay. So there are so many bottlenecks in the design of the analog IC design. Therefore the purpose here is not to horrify, but then to say, to glorify rather, that yes, wherever there is a challenge, there is opportunity. If there is only there is no much challenge, it is just more or less mechanical or just mundane, then probably opportunities are going to be less. Am I right or not? Or the remuneration also goes down, right? So now very quickly what we will do rest of the time, I also would like to mention about something about a mixed signal. So therefore in the beginning I said digital systems are very much required, right? Therefore now the bottom line is you need to have both digital systems and analog systems together, because in the signal chain, both at the front there should be analog subsystem, at the end there should be digital subsystem, and जो बीच का खेल है वो है तो मिज है, right? So that's what is total digital, right? Therefore what is jata sahi dhruva mrichu, right? Therefore you will take birth and then you have to just leave the world. Therefore these two are supposed to be there. Therefore analog processing is supposed to be there, and in between jo beech ka khel hai, that digital, right? That you are going to do. Therefore everything should be there. But what are the requirements here? If you try to see, they are different. For analog requirement and the digital requirements, digital subsystem requirements are different. For analog requirement, you have just seen that VDD as technology being scaled down, I will go for very small VDD, aisa nahi chalega. Therefore probably I have to use higher voltages, right? Power supply requirements are different for the digital. You may say, in the digital, can I just go down with the smaller scaled down supply voltages, right? In the digital, same signal to noise ratio, is it not a problem? Is a question. So in the digital, what will happen is ultimately you have to identify if there is 1 or 0, right? So this level or that level. Therefore still there is a room for you. However, there is a noise margin is going to be reduced, but then that is admitted. But still I can comfortably make a decision in favor of either 1 or 0. Therefore I can go with the scale down supply voltages. Therefore all the advantages of scaling down can be transferred easily to the digital subsystem design, whereas in the case of analog it is not the case, right? So therefore now putting both of them on the same substrate is a challenge here. The reason being, the digital nature of the digital subsystem is that it's 1010. You are switching all the time based on the input 1010, output also has to change, right? So the nature of the analog the digital subsystem is to switch between 1 and 0, right? So and when it is doing that at such a higher rate, then there is a capacitance which is always associated, right? Because there is when two metal types are separated by a dielectric, obviously there exists a capacitance. Therefore here on the same substrate there is always a parasitic capacitance. Therefore this switching signal gets coupled through this parasitic capacitance and it comes back, and both of them are the same substrate, remember, analog and digital. Therefore it comes under it comes and appears as the input to the analog subsystem, right? Analog subsystem actual input is very feeble, I said, no, very feeble, and I am going to just so clean cut. But then what happened now? This fellow, this switching noise. What is switching fellow? switching is a voice for the digital and noise for the analog. So switching is between what? VDD and ground. VDD and ground, such a strong one. One that is appearing at the input of the analog subsystem. Analog subsystem is taking very weak analog signal and you want to clean it and they want to, but then it's superimposed with what? This switching signal, which is between VDD and ground. Then what will happen? Gone. So therefore analog subsystem cannot distinguish and then it crips, right? It will not be able to do its job. Therefore there are many challenges here. Then what you have to do is, in the layout, the other day you might have seen the layout. So you have to protect the analog and digital subsystems in a beautiful fashion, right? So one should not hamper the operation of the other, right? Therefore you have to take special measures in drawing the layout. So you please remember that the analog or mixed signal operations are to be carried out in a very careful fashion. Every system which we are operating, every gadget is a mixed signal system only, right? So you have to protect the analog subsystem from the switching noise, right? So there are various measures for it, there are various ways of doing it, and the layout which you are going to draw, it's an art actually. We are going to which you have already experienced. So parasitic capacitance should be small and it should be compact, and then it should also provide a guarding, all these things. So therefore the design of the mixed signal IC design is indeed very challenging, right? So with that, let us do very quickly move towards the basic building blocks. Depending on the time permits, I will try to just touch upon. Actually I aim at looking at the characteristics very briefly, followed by the common source amplifier and its a variation, and followed by cascode, what the need of moving for another cascode, and then another topology, and then differential amplifier. These are the things which I am thinking. Depending upon the time permits, we will try to just close wherever it is possible. Let's just very quickly look at the metal oxide semiconductor. How it looks, as the name implies, the metal oxide and semiconductor, right? So this is a polysilicon, this is a acting like a metal, though it's not a metal, actually it's a misnomer, and then this is a p-type substrate, and this is n plus and n plus, this is source and drain. So please remember that there is physically there is no difference between the source and drain region. The source and drain are interchangeable, so both are n plus equally, and therefore depending upon the polarity that is being applied, source and drain are going to change the role. If one is positive, more positive as compared to the other, that is we call it a drain, because this is a n-channel MOSFET I said. So therefore that fellow is going to drain the electrons from that, whichever is positive, therefore we call it as a drain. Okay. So also you see that this is the effective length here, and this is a drawn length, because when the source and drain are being just now fabricated, then you can see that the diffusion or implantation, whatever it is, that may spill over slightly into the gate area as well. Therefore this is what is your overlap area. Okay, but you have to take that also into account. Therefore this is only the effective length is basically the total drawn length. Drawn length is the length which you and the mask you have just now drawn. This is the length that is you have to draw. You have drawn in the mask here. So from the drawn length you have to subtract the overlap area, right? That's what the effective length only you have just to take into account. Okay. So let's try to move ahead, and this is the NMOS and PMOS. Earlier what I have shown is NMOS, and this is the PMOS. In the case of PMOS, so there will be N well here, the PMOS in the sense it is a N substrate, and then P plus these are the source and drain regions, right? Now we want to have both NMOS and PMOS together, so this is called the CMOS, right? We are going to see the advantage of CMOS very soon. So therefore we want to have both, and it is allowing to do that, because I can take a P substrate and create a N MOSFET here, and now what I will do, I will dig N well and I will make my P MOSFET. Therefore both of them are sitting comfortably on the same substrate, and therefore the CMOS is there. These are the symbols, of course, you know, the MOSFET, N MOSFET and the P MOSFET, which you are well aware. So let's try to move ahead quickly, and so this all very quickly. I just now I will mention the MOSFETs are advantages for the digital. For the just briefly, we will try to mention a couple of things. There is a MOSFET. This integrated for technology. Is it suitable for the analog? Is it suitable for the digital? So, or both. We will try to just now spend some time. So the MOSFET's advantage in the most digital circuits do not translate to supremacy. Already I mentioned here. And the two types of circuits drawn upon different features of the transistor behavior. So the digital circuits, the switch, spending most of the time they spend in the stable states. On 1 or 0, 1 or 0. Transition is very, very small time, right? Right. So, therefore, while analog circuits depend upon the MOSFET behavior, which is held precisely in the switching region of the operation. If you look in the inverter, right, just to recall the transfer capacitor inverter is a on and off, right, in between the transition region, that is a undesired region for digital. You want to reduce that region as much as possible, but in the analog, that is the playground. There, because the gain is greater than 1 there. Gain is greater than 1, therefore you want to have that. You don't want these stable states in the analog, because if you give the input signal and then output is either 1 or 0 only, for then it doesn't mean, right. Therefore, we want that this region is only the playground for us, right. Therefore, both are, now we can see both are complementary to each other, the operations, right. So, the bipolar junction transistor has traditionally been the analog designer's choice here due to the because of the large transconductance and higher output impedance. So, therefore, BJT seems to be a favorite for the analog designers, but we will see whether it is MOSFET is really suitable for the analog design or not, right. So, MOSFET suitability for the analog circuits, if you want to see, nevertheless, MOSFETs are widely used in many types of analog circuits because of the certain advantage. What are the advantages? Let us see here, right. One of the fundamental advantages for the MOSFET here is MOSFET actually, any designer what he wants, right. It's not working. I want to just do some maneuvering, right. I want to just change something which free parameters he wants. You want to have a free parameter. What are the free parameters generally? Voltage, current, bias voltage, currents. Other than that, what else? You also want something else, right. You want to have more free parameters, which is an easy fashion you can do that. And MOSFET offers that beautifully, because by varying the geometry, by varying the W and L, so you are able to impress upon or vary effectively the performance parameters, particularly the transconductance is going to vary, right. So, the performance parameters of the MOSFET are going to change with the dimensions. So, as a designer you love it, right. So, that is the reason why we are going to use the MOSFET is actually, though BJT seems to be better from the current handling capacity, but then the MOSFET is really more handy for analog IC design, right. So, I said already that the characteristics of the performance they are designed by changing the sizes here, length and width, and so therefore, by comparison the BJTs probably they are not that sensitive to the device dimensions. Okay. Well, so MOSFET's ideal characteristics regarding the gate current and the drain source offset voltage also make them necessary ideal switch elements also. What not? I see the bottom line is I can design anything with the MOSFET, right. So, that is I can make switches, I can make right. So, resistor I can make, even passive elements also I can make, capacitor I can make, right. Of course, amplifier though it will behave anyhow, right. So, therefore, why not using the MOSFET, because it is going to offer me a good better leverage. So, in the linear region MOSFET can be used as a resistors and all, we are going to see, right. So, whatever it is, yeah, because just know, yeah, because I want to spend more time on the design, let me try to go ahead. So, I said that I can also use the MOSFET vertical, this all is not required, let me try to just go ahead. Yeah. So, you have already seen that there are advantages of the MOSFET for using to be used at the analog, but at the same time BJT is also we can't avoid it, right. So, because BJT is having very good current handling capacity, wherever it is required we will use BJT also. Then you may say that how do I put both of them together? By CMOS technology is there, which first if you try to open here you have the BJT models also and MOSFET models also. That means basically in this technology I can also fabricate BJTs, right. Therefore, we try to just go for both BJT and MOSFET together, right. And one more thing that I would like to mention here is the speed with which we are going to operate. Basically, what I said is by varying the dimensions I can just change the functionality, right. So, by varying W by L, in the sense what can I do, probably you are going to see later on that the resistance is inversely proportional to W by L. Resistance is 1 by mu C ox W by L into VGS minus V threshold. So, by increasing W by L I can reduce the resistance, right. So why you would like to just vary the resistance? If you want to increase the speed, you want to increase the speed of the device, then what you do, you just reduce the RC time constant, right? So that means you want to reduce the resistance, right? You want to reduce the resistance, then obviously what will happen is you are able to go for higher speed. So what you can do, probably you can just think of increasing the WL. But obviously what will happen, if you try to increase WL in order to reduce resistance, then obviously associated with the associated capacitance also will increase, right? Capacitance is epsilon naught A by D is Tox here, and area. So as you are increasing the WL or W or whatever it is, then what happens is the capacitance also increases. Therefore, as R decreases by some value, suppose R is halved, capacitance is doubled. So therefore, the advantage is not that it appears, but then definitely you can get the advantage specifically when the load capacitance is smaller, right? So this is what you can just see that later. And now yeah, let's move quickly towards the voltage current relationship here. So far what we have done is two things. One is we have justified the MOSFET usage to analog integrated circuits, and CMOS. Now coming to CMOS, CMOS is an automatic choice for the digital integrated circuit design. Why? Because most of the time you want either in the 1 or 0. So the CMOS, what it does in the CMOS design, if you are using CMOS technology, it is just like what is happening in the CMOS technology. Obviously, try to look into the inverter, whatever it is. So most of the time, either you are pulling it up or pulling it down. That's all, right? Therefore, it is an obvious choice, right? Whereas for analog, whether I can use CMOS or not is the question. Still, you can use CMOS for the analog also, which you are going to see it later on, right? So, and now coming to the MOSFET, which is driven by the voltage, we are going to derive the voltage current characteristic, which is very important for us to just go ahead for the analog design. So very quickly, let's consider the simple MOSFET here, right? When you applied some voltage, a positive voltage here, what is going to happen, right? What is going to happen? So you can just think that you may also ask another question: why silicon? Why silicon for the substrate? Why silicon for the substrate? That means in the CMOS technology, you are using silicon, right? So why silicon is the question? Why silicon is the question, right? And the other one is in the insulator, whatever for the insulator, you are using silicon dioxide as insulator, right? Silicon dioxide, actually there are better insulators. There are better insulators, but why are you using silicon dioxide? Is the question. Silicon is of course a good semiconductor, but then people are now exploring towards what are the other semiconductors possible. But the question here is silicon and silicon dioxide combination. What is the purpose of using it? It is just they're going to match each other, right? So just like now I keep on quoting this example. Suppose you are asked to have, there's a milk which is boiled, right? And there is a cream on the top of that. Cream is created because by cooling it or annealing it, you have got a cream that is formed, right? Not the packet milk, try to get some good milk from outside. Then you'll get a thick cream on the top of that, right? This is automatic. When the boiled milk is cooled down, the thick layer of the cream is formed. Now you want that put pepper and all, right? So somehow you want a decoration, whatever you call. You don't want that it should be mixed before. So therefore, the pepper powder is on that, and we are going to keep that, right? So then what happens now? In the place, because you want to separate the milk with the pepper powder, then what are you using here? The cream of the milk. Instead, if you use any other material, it is going to spoil the characteristics of the milk, right? Therefore, it is always better to use a separator which is not going to intervene with the characteristics of the milk, right? Similarly, here also, what we are doing is the same silicon is oxidized, right, using the mask. Therefore, silicon oxide is going to act as the insulator, but then the interface between the insulator and the silicon or the whatever the semiconductor is not what you call abrupt, right? So that the hanging bonds, these are called dangling bonds, right? So they are minimized. Otherwise, if you use anything else, what will happen? These covalent bonds will be abruptly open and they'll be hanging, just like akarsha. When the electrons are moving from source to drain, then they'll get trapped into those, and therefore, obviously, you can think that the current that is actually you're going to receive is not proportional to the signal voltage, right? So now also that phenomenon will be there, but it will be minimum, right? So therefore, because of this compatibility and self-alignment, we try to make use of the silicon dioxide as the insulator, right? Now let's try to come here. So when the gate voltage increase from 0, what will happen? What will happen? This is the p-type substrate. The p-type substrate, what are there? Immobile holes are the majority carriers, and then immobile ions are there. Immobile acceptor ions, right? Now, so when the voltage keeps on increasing, applied voltage, what will happen? What will happen? These holes, they get repelled back down, right? So the holes get repelled, therefore they leave behind the acceptor ions. They leave behind the acceptor ions. So these acceptor ions, therefore you can see that this region is now depleted of majority carriers, which are holes, and therefore we say that depletion region is formed. Am I right or not? Depletion region is formed. Is it okay? Right. Let's try to move ahead. And so this depletion region, now obviously please see that though I have made drain positive with respect to source, no current flows, right? No current flows, right? So then what happens? As Vg increases further, what will happen? As Vg increases further, I am trying to increase Vg further, right? So what may happen here? The potential at the oxide silicon interface is going to increase here. So the oxide in the sense silicon dioxide, okay? And the structure resembles two capacitors in series. So one is the gate oxide capacitor and the depletion region capacitor. This is capacitor in the sense what? It is basically two metal types which are being separated by dielectric, right? They are, so silicon dioxide is separating, therefore that's one capacitor you just think of, and then there's a the depletion region is there, therefore by the virtue of the depletion, now that separation is now depletion region separation, therefore there's a, because obviously the magnitude of the capacitance depends upon the distance and also the nature of the dielectric also, right? So therefore it is a depletion capacitor, right? Now if you try to increase further, so when the interface potential is sufficient to reach, then what will happen? What will happen? Now let's try to see, as you keep on increasing the positive voltage, what will happen is, now earlier though I didn't mention, but then even when the applied gate voltage is even small, then the electrons, however small they are, they start moving from substrate and they start moving towards the oxide silicon interface already. However small they are, it is a continuous phenomenon. It is not that all of a sudden like that they will go. So continuously 1, 2, 3, 4, whatever it is, they keep on moving. But then at a specific value of the gate voltage, you can find them significant number of electrons have reached the oxide silicon interface, right? So but then in the beginning, what is the hindrance? What is the hindrance for them to flow? What is the hindrance? Hello? What is the hindrance for the electrons to move oxide silicon? You are a MTech student? Final year BTech, okay. You have taken CMOS course already. Okay. So what is the hindrance for the electrons to move, reach the oxide silicon interface? So the depletion region, sense these immobile acceptor ions, they are negatively charged, right? They keep on repelling them. Therefore, for the electrons to reach the oxide silicon interface, that positive, that attractive charge, the potential should be sufficiently large to pull these electrons to overcome this repulsion from the negatively charged what is this? Acceptor, immobile acceptor ions, and then yet they have to reach there. That is why there is hindrance, otherwise immediately they would have gone. Therefore, they gradually reach the oxide silicon interface, right? So now what happens? For suddenly you find that gradually they are coming, and this region near oxide silicon interface is full of electrons, right. So if you observe closely only this area, this appears to be what? Only electrons are there. Only electrons are there, right? Oh, you think that it's n-type semiconductor, right? That region only. If just to put zoom and see, only electrons are there. If you say it's n-type semiconductor, it appears to be, right? Therefore we say that this region, the oxide silicon interface is fully inverted. It is fully inverted, right? Therefore, the interface is fully inverted. Then we say, then that moment we say, yeah, now the transistor turned on, because I got sufficient electrons for them. If it is made positive, they start moving from source to drain, right? So this is what is the right. Now let's say to define the threshold voltage. All right, what is threshold voltage? Now we have to define threshold voltage, right? Generally we can speak. What is the threshold voltage? You have to define a threshold voltage. How do you define? Minimum voltage required to form a channel, or you can say minimum voltage required to turn the transistor on. All these things are beautiful statements, right? All these are beautiful statements. But now you are dealing with the systems, right? So system doesn't understand what it is. Okay. So if your father asks, beta, you are going to college. Okay, what is the money you want now? Pocket money, right? Whatever you can give, Papa. If you say, whatever is required for my expenses, there is not. You have to quantify it. You have to quantify. You have to 10,000, 20,000, right? This month there are parties. So therefore, you should mention it, quantify it, no? So for the tool, because you are simulating it, right? You are in the model, you have to specify that above this voltage, the transistor is on. That means in the equation you have to just give that value. Otherwise, computer doesn't understand, right? So you have to quantify it. So how do you? Because you have seen actually that the electron is a continuous phenomenon. The electrons are moving from the substrate towards oxide silicon interface before the birth of the Christ itself, because you turn the moment you have put the voltage made positive, there is always a 1 or 2 they keep on moving. Okay, so this didn't happen all of a sudden, but then some reasonable number of electrons when they have reached, then we say transistor is on, right? So you should quantify, you should give an expression for the threshold voltage. How do you do that is the question. How you should give an expression, you should quantify, right? How do you do that is the question. You just can't say just no like that. Already I have given a hint. What is the hint that I have given? At BTech boys, सीमा से पढ़ा था. Don't just make it complicated. I just okay. So without losing time, just to say that the oxide silicon interface, I said it's inverted, right? Right. So inverted in the sense it's acting like it appears as if it is n-type silicon, I said, right? So n-type silicon, I said, but actually substrate is what? Substrate is p-type. P-type in the sense it is doped with some boron, gallium, indium, whatever it is, right? Trivalent impurities. So it is already doped with some doping concentration. You know that. You know the doping concentration of the p-type substrate. That's what is a known thing. Now this again, what is there in the top here? This area. This area is also substrate. It's not nothing somewhere. It has not come. This is the same substrate, here also it is there, but this area is now full of electrons. It is as good as now, it is now behaving like n-type silicon. Therefore, that is a catch for me. I can now say that the threshold voltage is the voltage that is required to make the oxide silicon interface as much n-type as it was originally p-type. As much n-type as it was originally p-type. So that means The doping concentration you know now, therefore you can always say that you can relate the applied voltage with the doping concentration of the p type and then just arrive at a value. Is it okay or not? In terms of the known value doping concentration of the p type substrate, I am able to express now the threshold voltage. Is it okay? Does it make sense? Right. So this is what I just mentioned. Okay. So this is the gate to source voltage. This is the gate voltage that I am going to apply at the in such a way that the oxide current interface is as much N-type as it was originally P-type. So this is the quantification. We will not go much into the details. Here's the job of the device modeling. Therefore, we will try to take the fruits granted that, but I can say that it is a function of the work function between the metal and silicon, and then this is the work function, and then this is a function of doping concentration as well. Okay, so this is N sub, right? This is doping concentration. Okay, obviously, the lighter the substrate is doped, the depletion width will be larger, right? So you have to apply more voltage at the gate to pull more, same number of electrons. Am I right or not? If the gate is relatively little bit more doped, then what will happen? Then I need to apply less voltage only. Therefore, obviously, the threshold voltage is a function of doping concentration of the substrate. Am I right or not? So, having said that, I just also mentioned that suppose you calculated, then you based on the doping concentration, suppose 0.7 volts or whatever you got. But then after fabrication, during fabrication, you may not get exactly your book value. Then you should have some way to control it and to have a precise value, right? Calculation is different, right? But then the way it just now the actual value probably may slightly differ, but you want to have that calculated value. Therefore, what you do during the fabrication, you try to maneuver here, use some P plus doping here, you try to control to have a precise value of keep on iterating, right? So probably in the scaled down models, you can apply AML and then see that all the statistical things, and then see that more precisely can I get or whatever it is. That's what exactly people are doing. What they're doing is the earlier models, that, for example, the 40 nanometers or even what about 130 nanometers, 45 nanometers. They try to just take all the behavior and all, try to put the statistical model and all, make use of it, and then try to apply AML model, apply the these algorithms, and try to have a prediction about for the scale down technologies, so that they can quickly arrive at the value instead of wasting more time, right? Very quickly, let's try to just now look at now we'll try to derive the current voltage relationship for the MOSFET very quickly. So let's try to consider semiconductor bar which is carrying current here. This is a semiconductor. After all, the MOSFET, the substrate is semiconductor bar only. Break, huh? Okay. Let's break. Generally the density is per unit area, that everyone knows, but here we are deliberately we are choosing it to be per unit length. Per unit length we are choosing for the reasons that we are going to see later on. So the density is per unit, QD is charge density per unit length. So velocity of the charge of course is v meters per second, and therefore QD is QD coulombs per meter, that is what the charge density. And let us try to just measure the total charge that passes through the across a cross section of the bar in the unit time. So with the velocity v, okay, then all of the charge that is enclosed in the v meters of the bar, it must flow through the cross section in 1 second, right? Therefore I can say that I is equal to QD into v. What is v? Velocity. Velocity is meters per second. Am I right or not? Okay. So QD into P. Is it okay? So the current is Q is equal to IT. Q is equal to IT. So then it becomes what? IT into meters per second. So therefore it will be the charge, right? Therefore the corresponding current I is equal to QD into V. So therefore what will happen? Now let us consider the MOSFET like this. Earlier what we have done is we have given some positive voltage to the drain. Now deliberately we are not giving those your necks will pain. You can come forward and sit here. You can come forward and sit here. If you are tall enough, it's okay, but you are tall, all right, but then not that tall. Right. So now deliberately we have connected drain to the ground and source is also at ground. Therefore, what it implies is whatever you do, then current will not flow from source to drain. Okay. Now we are giving voltage at the gate, and then we would like to just see what is going to happen, right? So what happens now? What is the channel charge density in the inversion layer? So what is the channel charge density in the inversion layer? So we know already, we have seen that we have declared the channel is formed only when applied gate voltage is greater than threshold voltage. So when VGS is greater than threshold voltage, then only channel is formed. Therefore, whatever the channel charge density, in the sense whatever the electrons which are the density of these, is proportional to what? It is proportional to the applied gate voltage over and above the threshold voltage. If the applied gate voltage is less than threshold voltage, we are not considering that there is channel. We are not considering that there is any channel, right? So when the applied gate voltage is greater than threshold voltage, then what is happening? The channel charge density is increasing, right? The channel is formed just at the threshold voltage, and over and above, if you keep on increasing further, then the channel electron density keeps on increasing. Therefore, channel charge density increases. That means the channel charge density, I can assume that it is proportional to VGS minus V threshold. It is proportional to the gate to source voltage, which is over and above the threshold voltage. Okay. So channel charge density is proportional to VGS minus V threshold. Is it okay? All right. So for now this yields now when we have just now made this drain ground deliberately, then the channel charge density is uniform along the length of the channel. It is because no current is flowing there, no drop is there. Therefore, it is uniform along the length of the channel, right? Now, what I will do, since I said that the channel charge density is proportional to what? It is proportional to VGS minus V threshold, right? And I know that Q is equal to CV. I know that Q is equal to CV. So, C, this all is C into V is over VGS minus V threshold. Why the C is like this? You have mentioned. The reason being the capacitance is the oxide capacitance, because it's by the virtue of the separation between the polysilicon, that is gate, and the whatever the substrate is there. In between, what is separation? Silicon dioxide. Therefore, we say it's oxide capacitance, C ox, right? This capacitance is a function of area, right? So the larger the area, the larger the capacitance it is, right. C is equal to epsilon naught A by Tox. So therefore, and in the design you try to change the W by L, right. You keep on changing the dimensions. Therefore, capacitance also keeps on changing. So there is no point in mentioning the absolute value of the capacitance. Rather, if you try to mention per unit area, then depending upon whatever is the area that you are going to choose, the absolute value you can calculate, right. Therefore, it makes sense to express the capacitance as per unit area. So Cox is the capacitance per unit area, right. But then what is channel charge density? It is per unit length. So if you multiply Cox with W, then what will happen? Cox into W. Cox is actually capacitance per unit area. So if you multiply, then you will get capacitance per W into, this is actual absolute capacitance per W into L. W gets cancelled. So it is capacitance per unit length as required, because we have said that QD is a charge density per unit length. Therefore, okay, so Cox and W is C total by L per unit length, because QD is also per unit length. Is it okay? Right. So let's try to move further. And now what we have done earlier, drain voltage was grounded, therefore uniform channel charge density was there. Now I am going to make the drain voltage to be greater than 0. When the drain voltage is made greater than 0, right, then what is going to happen? Okay, let's try to just see that. For that, see, you have applied the drain voltage here. Okay, now see, the channel potential varies from what happens to channel potential? It varies from 0 at the source and to the VD at the drain. You can just think of between 2 points VD is applied. For example, terminal A is there, B is there, between that some voltage is applied, right. So here there is a resistor, just think of. Then what will happen is, for example, 5 volts is applied at VA positive 5, and with reference to VB it may be 0, whatever. Then this potential, what happens? It keeps on getting dropped along the length. Am I right or not? It keeps on getting dropped because after the resistor it is. So wherever it is full 5 volts is there, and in half of the way through, when the length is half exactly, the voltage is dropped to half. Then it is a 2.5 volts, and if you come down further, it is 0 volts. Therefore, the potential keeps on getting dropped along the length of the resistor. So your channel can be viewed as a semiconductor ball. It is just simply like a resistor. Therefore, if I apply some voltage between the drain and the source, then this potential keeps on getting dropped along the length of the channel, and here at the drain it will be maximum. Suppose if I apply 5 volts, here it will be at this terminal it will be 5, and then half the way through it is 2.5, and when we reach the source it will be 0. So therefore, the potential VDS is now getting dropped along the length of the channel, right. So therefore, at any point along the length of the channel, let us say arbitrary point, let us say X here, right. So where Vx is the channel potential to X here, so I can say that, as I mentioned already, local voltage difference between the gate and the channel varies from Vz to Vz minus Vd. So at any point, what happens at any point on the length of the channel, what is the voltage? Already some potential I am going to apply from gate here, and some potential between the drain and source. So net whatever it is Vz minus Vd. So therefore, now the current density is what is it? It is W Cox into, it is I said earlier, Vgs minus V threshold minus V of x, where V of x is your the potential at x here, right. So it is ID is equal to minus actually signifies that it is a electron current, right. Therefore, the ID is equal to minus W Cox into Vgs minus Vx minus V threshold into V, right. What is V? V is velocity, right. So QD is equal, you already seen that V is velocity, right. Well, so now what is velocity? Velocity is equal to mu into E, very easy, electric field, right. So I can write that QD is equal to W into Cox into Vgs minus Vx minus V threshold, and further try to substitute the V here. So it is V is mu into E. Is it okay? Right. Now further what will happen? ID is equal to, I will try to substitute in the place of the E, electric field is expressed as dV by dx. This all you know, right. So this is a minus dV by dx, minus gets cancelled, it becomes plus. Okay. Now, so as I already mentioned, the length of the channel is x, I said, So when when starting at the source, let's say that length here, starting point is 0, and at the drain the length is L, 0 to L. So therefore, at any other point it says arbitrary value is x, right? Therefore, I am expressing V of x as V of 0. At 0 the value is 0 because I said that VDS is totally dropped there, and at L the applied voltage is VDS. We have said that V of x is a function of the length there, right? VDS is maximum at the drain and minimum at source, right? So now we will try to integrate this both sides. Let's integrate this equation both sides. So take this dx this side, take this dx this side, and try to integrate. What are the integrating limits now? With respect to x is coming here, so x limits are from 0 to L. X limits are 0 to L, right? And on the right hand side, the limits for this voltage, right? That is V of x is varying from, when x is equal to 0, what is V of x? 0, and at x is equal to L, what is V of x? VDS. Therefore, the integration limits on the right side will be 0 to VDS. So just try to do the integration, right? So you will get, this is the integration here. So I will try to do the integration and all. There is simply here, since ID is constant like the length of the channel here, so what you can just now find is, just you can do quickly the integration. Okay, math you can always do. VGS minus Vx minus V threshold, the VGS minus V threshold into, because integration into V you will get here, right? And minus, this is a V of x is V is V square by 2, and if you have to substitute the limits here, so when x is equal to 0, the value is 0, right? And x is equal to L, the value is VDS. So therefore it is VDS, and it is VGS minus V threshold VDS minus VDS square by 2, and the L is ID is integrated here, so it is simply L minus 0, so it is L here, right? That L comes here, and therefore current is mu Cox W equivalent to VGS minus V threshold into VDS minus VDS square by 2. That is the current equation. So it appears that beautifully when a voltage is applied at the gate, so you can find that the current is varying this way, right? Okay. So the bottom line here is how it, if you have to plot it, how it appears. Yeah, it appears to be a parabolic equation, right? It appears to be a parabolic equation. So the current is varying in a parabolic fashion. What is this current? Can you please tell me the current between source and drain, right? So the variation we are trying to see for a given gate voltage. Now we are not varying gate voltage. We have fixed the gate voltage above the threshold voltage, right? For a given gate voltage, we are varying the current with respect to what? VDS, right? As VDS is a parameter now, as you are varying VDS, how the current varies, that's what is the description here, right? So L is always effective channel length. Therefore, if you try to plot it, it appears to be parabola. Now, as VGS is being varied, they will get different family of the curves here, right? You can anticipate that. The higher the value of the VGS, what will happen? So the moment it is parabola, you can anticipate that there is some maximum value of the current. After that, it is going to decrease, right? So then you can see as VGS is being increased, the maximum possible value of the current is also being increased. What could be the reason? Just a simple, it makes common sense that as VGS, for higher VGS, what should happen? The higher the VGS, the higher the channel charge density. The higher the channel charge density, the larger the current. You can just think this way, that as the gate to source voltage is increasing, just think of, if gate to source, for a given gate to source voltage above threshold voltage, some channel is formed, right? As the applied gate to source voltage is increasing beyond that, what will happen? The channel charge density keeps on increasing. I always keep on quoting this example. Try to look at the clouds. The cloud, when the clouds are becoming thicker and thicker, then when the moment the air is getting added to it, and obviously it rains heavily, right? When the air gets added to it, it rains heavily, right? So जो बादल है जब और भी घना बन जाएगा, then what happens? बरसात भी भयंकर होगा. It will be right. So therefore, it is a proportion. What is happening? The applied gate voltage is now proportional, or the channel charge density is proportional to the applied gate voltage over and above the threshold voltage. Is it okay or not? Right. So what is the air, whatever I said, it corresponds to what here in our context? When the current flows, see, if the channel, if you are increasing the gate to voltage, gate to source voltage, then channel charge is increasing and increasing and increasing. But when the current flows, only when the drain is made positive. जब बादल घना बन जाएंगे तो वर्षा नहीं आएगा, तो इसके साथ हवा जोड़ना है, right? So therefore, here when VDS is made positive, then it just takes away all this. But then how much maximum current, it depends upon what the channel charge density, right? So for a given VGS, whatever the channel charge density, to that extent only the current flows. If you increase VGS, then because channel charge is increasing, then the maximum possibility of the current also increases. Am I right or not? Therefore, maximum possibility of the current keeps on increasing as you are increasing the gate to source voltage. Am I right or not? Okay. So that's what exactly I mentioned there. Here the point from here, what you have to just take away once again. The question arises, though I have mentioned some values here, obviously you will be curious to know when the current will be maximum, number one. When in the sense for which value of the VDS the current will be maximum, right? It's a question. Number two, in which case what will be such maximum value? There are two questions which you are supposed to answer. For which value of the VDS the current is maximum, and what is that actual maximum value? They are the two things that you are supposed to look at it, right? How do you calculate? Of course, a simple math reveals that maximum in the curve we can always find the maxima. How do you do that? How to do that? By load. The mathematical equation is there. You want to find the maxima. What you will do? Mathematical equation is there. You want to find the maxima. How do you do that? By standing upside down. Math. I mean nothing else, only math. Equation. By differentiating and equating to 0, so you'll be able to do that, right? So exactly the same here. So calculate dou ID by dou VDS. This is a partial differentiation of dou because current is also a function of VGS. We are keeping the VGS constant. So the dou ID by dou VDS is equal to 0. The same equation, whatever it is there, you just do the partial differentiation and equate to 0, right? So then you can do that if you want to do quickly. Here, what is the equation? Equation is ID is equal to mu C x W into VGS minus VDS into VDS minus VDS dou ID by dou VDS. So then what happens? With respect to VDS I am trying to do, therefore this all is constant, you know, it remains there. And then what is there? Dou ID by dou VDS means this becomes dou ID by dou VDS, right? So therefore it becomes VDS, right? Simply 2 gets connected to VDS. So it is VDS. So VDS and equal to 0, therefore VDS is equal to VGS minus V threshold. Okay, with respect to VDS you are doing, this is 1. The scaling factor remains there. VGS minus V threshold minus VDS is equal to 0. So VDS is equal to VGS minus V threshold. So therefore you can say that for VDS is equal to VGS minus V threshold, I will get maximum value of the current. Alright. So not happy? मैथ तो थोड़ा सा करना पड़ेगा, हाथ कलम लेके किताब में खड़े दे तो then it will be more, you will be satisfied, right? But then so since we don't have time for you to just know to allow to do that, but then just know, right? So this is the VDS. Now for this value of the VDS, what is that maximum value? Then what I do? You have to substitute this back into the current expression. So if you substitute back into the current expression, I'll get it as half mu C x will do VGS minus V threshold whole square. If you want, you can see that quickly. So look at this expression. So in this expression, what I will do, I know that for VDS is equal to VGS minus V threshold, I will get the maximum current. So substitute that here. This becomes VGS minus V threshold into VGS minus V threshold. VGS minus V threshold whole square. So this is a VGS minus V threshold whole square by 2. Then it becomes half of a VGS minus V threshold. So therefore, I can say that the maximum value of the current is half mu Cox into WL into VGS minus V threshold whole square. So this is simple. So simple math is nothing much. Right. Now, alright, I got maximum value, or what is maximum? Now, the question here is, suppose I will just know, sorry, I have to just go here. Yeah. If I focus on this region, right? If the applied VDS is far less than VGS minus V threshold in this region. In this region, what will happen? The current is, I just want to see what it is. That means when VDS minus is far less than VGS minus V threshold, or I can also just try to look at this equation where this so this equation I'll try to multiply this to take LCM here. This is 2 into VGS minus V threshold into VDS minus VDS square whole divided by 2, right? Okay. Now I'll try to compare this VDS square with respect to 2 into VGS minus V threshold, right? So if VDS is far less than that in that graph, right? When VDS is far less than 2 into VGS minus V threshold, if VDS is far less than 2 into VGS minus V threshold, right? Then what happens in that equation? You can see far less than, since VDS is a fraction, 0.1. So 0.1 square means what? It is further smaller, right? So it's smaller. Therefore, what I can neglect it. Am I right or not? Is it okay or not? So when VDS in that equation, when VDS is for the two things A and B are there. So one it's called something A minus B, and B is very small as compared to A, and its square obviously will be further small. Therefore, I can neglect that. Am I right or not? Therefore, I can now approximate in that condition the current as ID is equal to, when you neglect it, it is simply, what is that equation? Mu C of W into VGS minus V threshold VDS minus VDS square by 2. So therefore, VDS square by 2 gets cancelled. I am neglecting it. Therefore, what is left over is simply mu C of W into VGS minus V threshold into VDS. Therefore, in the region when ID is when VDS is far less than VGS minus V threshold, then we say it is in the linear region. Why it is linear region? ID is proportional to the VDS here. You may also say, yeah, it's a function of VGS also, but we are keeping VGS constant here. We are not talking anything about, because it's just like a semiconductor board between the two terminals A and B, source and drain. So between that, some voltage is applied, VDS is applied. I am varying it, right? Now how is the current is varying? It is simply varying linearly. So it is following which law? Ohm's law. So therefore, it is just acting like a resistor, right? It is just acting like a resistor. What is the corresponding value of the resistance? If you want, simply VDS by ID is equal to 1 by mu C of W into VGS minus V threshold, right? Therefore, I can say that the resistance is 1 by mu C of W into VGS minus V threshold. So therefore, I can say that it is just in this region. If you zoom and see, it is acting like a resistor, and this resistance is a function of what? W by L. Larger the W by L, resistance will decrease, because resistance is equal to 1 by mu C of W by L into VGS minus V threshold for a given VGS, right? So therefore, I can say I can use it as a variable resistor as well, and I can use this. This is a linear region. This is the linear region, okay? So I can use it as control resistor or a switch also, right? Therefore, by varying W by L and all. So therefore, I can always say that whenever I want to have I want to short it, then I'll try to just use a larger W by L, and I want to use open, then use larger W by L, smaller W by L, right? So this is what is now. If you want, you can see the variation of the R on with respect to VG also. You can see this example what I am trying to do here. What is being varied here? So this is with respect to VG, I want to plot R on. With respect to VG, I want to plot R on. Okay. So how do you do that? When VG, with respect to VG, when let's assume that threshold voltage is 0.7 volts. Assume that threshold voltage is 0.7 volts. Then the transistor will be on when what is given here? Additionally, one source is connected. Where it is connected to the source. At the source, one voltage source is connected. Therefore, now that means when the transistor is to be on, then this is 1 volt. That means this VGS should be greater than 0.7, I said. So what is VGS here? Already at the source 1 volt is there. Already at the source 1 volt is there. So VG should be greater than 1.7 volts. Then only the transistor will be on, right? Therefore, the VG should be greater than 1.7 volts. Then transistor is on, and if you keep on increasing gate voltage, you have seen that it is also inversely proportional to gate voltage. Resistance is 1 by mu C of W into VGS minus V threshold. So therefore, the resistance keeps on decreasing. Not only mathematically, conceptually also you can say that the gate voltage is increasing, channel charge density is increasing, right? Therefore, the current is also maximum possible, right? Therefore, obviously resistance is smaller, right? So that's what is the case here. Now, so you have seen the left side of the characteristic equation. Now, if you try to move on the right side, That is, it is actually what is the current equation? It's a parabolic equation. So ID is equal to mu C octave divided by VDS minus VDS only VDS minus VDS square by 2. So as VDS is greater than VGS minus V threshold, what is going to happen? Let us see. We have far less than we have seen. But greater than that, actually, what to see? You may say that it's falling, not falling, but really it falls or not the question. Probably it may not fall. Let's try to explore it, right? So whether it is really going to follow the parabolic path or not is the question here. So why it is not following parabolic path? Actually, what is going to happen? Let's try to see here. So it is going to be a constant right there. Okay, it is going to be constant after VGS minus V threshold. So why it is not falling is the question. Let's try to just now see very quickly. Okay, so let's try to just look at this. What is happening here? So the density of the inversion layer. If you, I already mentioned that the voltage VDS is actually dropping as you are moving away from drain to source. Am I right or not? So I said the channel charge density, the inversion layer is proportional to VGS minus Vx minus V threshold, right? So what is the Vx here? I said if Vx is varying, right? Vx is varying. What is Vx? Vx is your drain to source voltage, right? It is now a function of the length of the channel. It is maximum at drain and 0 at this point, right? So therefore this fellow is varying. Vx is varying. Now that's a drain voltage. Now as the drain voltage, but the drain and source voltage, if that is now because it's varying, let's say that an example is just now mentioned here, VGS minus V threshold suppose is equal to 1 volt, right? VGS minus V threshold is equal to 1 volt. Okay. So when VGS minus V threshold is equal to suppose 1 volt and VDS is suppose varying. When VDS is varying, okay. So then what happens? This is a VGS minus V threshold 1 volt and VDS is suppose only 0.5 volt. This is 0.5 here. It's applied, right? So it's a 0.5, it's a 0.25, and this is 0. It's 0.5, 0.25, and 0, right? Now, as the VDS is increasing, let us say VDS is equal to 1 volt now. VDS is increasing. Let's say VDS is equal to 1 volt. When VDS is equal to 1 volt, that means at this point, it is 1 volt, right? So at this point, what is QD? QD or it is basically, it is proportional to VGS minus Vx minus V threshold, right? VGS minus V threshold is 1 volt and Vx is also 1 volt because I applied VDS as a 1 volt. At the drain, Vx is VDS only. So this is 1 volt. 1 volt minus 1 volt, how much it is? 0. That means at the drain, when the drain voltage is equal to VGS minus V threshold, that's why actually I am trying to increase. When reach that, then what happens? QD is equal to 0. When QD is equal to 0 means what? There is a channel. Channel got extinguished. Right? So at this point the channel is extinguished. Suppose if I keep on increasing this drain voltage, let us say now it has gone to 1 volt, I said at the drain. Now let us say it is now 2 volts. Right? If it is 2 volts, then somewhere in the middle it becomes 1 volt. Right? Somewhere in the middle it becomes 1 volt. Right? So till at this point it is QD is 0. Beyond this QD is 0. Am I right or not? Because QD is proportional to what? VGS minus V threshold minus V of x. So the point where the extinction took place now has moved away from the drain toward the source till the middle point, right? So the channel charge density becomes 0 throughout all this point. If I try to increase this further, right, let's say now it is earlier how much I said? 2 volts. Let's say it is suppose 3 volts. When this is 3 volts, then what happens? So middle is 1.5 and somewhere here it will be 1 volt, right? Somewhere here Vx is 1 volt. So at this point channel becomes 0, right? Because at this point it is equal to VGS minus V threshold 1 volt. So the point where you can see it is getting pinched off, it keeps on moving away from the drain toward the source. So the point where the channel is getting extinguished is moving away from drain toward the source, right? So understood or not? Okay. Therefore now that which implies that the earlier equation whatever you thought not valid, not valid. Actually what is going to happen here, magic is, you may ask, then current may not be there and then channel is got extinguished, then what? It doesn't happen that. Actually the channel, mathematically we don't see, conceptually we will see here. So what is happening, the channel is getting pinched off all right, but then see, suppose the channel is got come here, right? So but then there is electric field between this point and this point, because what happened, applied VDS is more now, applied VDS is more, right? So to which extent the applied VDS is more, then with that whatever is the additional electric field is there, it will pull the electrons from this point, from wherever it is pinched off toward this. So the channel ये कितना पीछे जाएगा, then उतना electric field will be more, right? So it will try to pull the electrons with the increased electric field. Understood or not? So therefore, actually what is happening, the additional applied voltage VDS is now being spent in pulling the electrons. So the current is constant. Understood? So the point is, as VDS is earlier, incremented VDS is also causing more electrons to come to here. But now what happened? The electric field is increasing, as VDS is increasing, but since the channel is pinched off, now that point is now moving away from drain to source, and therefore the increased VDS is now actually making causing the electric field to increase, and therefore that is spent in pulling the electrons from the pinched off point towards this, right? Therefore the current becomes constant, right? So this is what is it will not fall, rather the current becomes constant beyond the pinch off. Is it okay? Right. So this is what exactly whatever I said there. Okay. It's okay? Right. So therefore now what it implies is that the model which you have thought, what is that? ID is equal to mu Cox W by into VGS minus V threshold into VDS minus VD square by 2 is not going to be valid anymore now. Therefore you are supposed to go and again remodel it beyond the pinch off point, beyond when VDS is greater than VGS minus V threshold. Till that point the same model is valid, but beyond that it is not. Therefore you have to go and revisit that equation, right? So therefore recall the equation for the current here. I is equal to, what is this current equation? Actually we have thought it's a W into Cox into VGS minus Vx minus V threshold into mu dV by dx. Okay. Now what is the difference here? What is the difference here? The length is not L here. The length is changing. Channel length is getting constricted. Am I right or not? Let's say L dash. Let's say L dash it is. Okay. So now the integration now is to be taken place from x is equal to 0 to L dash. 0 to L dash I have to take here. So now I will try to redo the calculations here. So I know what is L dash. L dash is the point where the channel is pinched off, okay, or QD is becoming 0. So if I try to do that, then the limits are from V of x, that is VDS is now V of x is equal to 0 to up to which point I have to take now? L dash only, na? L dash only. At source it is 0 anyhow. So that V of x when you try to consider, at x it is 0, therefore at V of 0 is 0, no issue. But where I have to consider now? At x is equal to L dash I have to consider. At L dash, what is the value here? That VDS is VGS minus V threshold, because that value is equal to VGS minus V threshold, therefore channel is getting extinguished, right? Therefore that is V of x is equal to VGS minus V threshold. So we have to use these two in order to calculate it. Therefore in the same expression go and do the integration again there, right? And if you substitute 0 to L dash, and then in the left side in the equation here use here from 0 to L dash, and here I will try to do the integration from 0 voltage from V is equal to 0 to VGS minus V threshold. Then simply I will get the equation as half mu Cox W by L dash into VGS minus V threshold whole square. So in the saturation, this is called, this reason we say saturation, because the current is now constant. Even VDS is varying, you can see that there is no function, there is no VDS at all. Even VDS is increasing, the current seems to be, I am very careful in using the words. So current seems to be constant, but the current is not increasing here, right? So mu Cox W by L dash into VGS minus V whole square, right? So therefore I can plot the current as a constant horizontal line, right? But having said that, if someone carefully observes, you said that L dash is there, right? L dash is there. L dash is not constant, right? So as VDS is increasing, L dash is it constant? Actually, what is happening to L dash? Varies already. What is happening? Varies means badega ghatega. Whether it increases or decreases? L dash decreases. So L dash is decreasing. L dash is decreasing means the current is it constant? Dhoka ho gaya na. So therefore, we said that current is constant, right? Because I said explicitly VDS is not visible. Explicitly VDS are, mutual funds are very sahi hai, mutual funds sahi, investment sahi hai. People say then risk. So they say that, right? So therefore, I said that current is constant because it's not a function of the VDS here, but it's implicit. Implicitly, because L dash is decreasing, as VDS is increasing, L dash is decreasing, therefore current is increasing. So ID is not constant actually, right? But however, having said that, we'll say that, we'll take it granted that when this L dash variation not that much, we have to justify, na? When L dash variation not that much means which much is the question, right? So as compared to the length of the channel, if the L dash is very small, not L dash, variation, I say delta L. If the variation delta L, let us say, if the variation delta L is very, very small as compared to the full length of the channel, then I can ignore it. Am I right? Or I can ignore it. If, for example, if I say, then no, I am going from wherever, suppose you are staying in the hostel somewhere, here, NIT Warangal hostel, to, you have to go to Hyderabad, right? You hired a car, right? So then that fellow now, he says that NIT Warangal main gate to Hyderabad, or otherwise Kazipet station to Hyderabad, right? So you may say that you started from this one, but I have to calculate from Kazipet to Hyderabad. It should not matter because this distance is only as compared to 150 kilometers. This is only a matter of half kilometer or whatever. So probably it is negligible, right? So therefore we just now ignore that. Similarly here, this variation, if the length of the channel is large as compared to the variation delta L, we ignore this and we say that current is almost constant. So we will just not take it granted, right? This is what. Okay. Well, so these are the observations here, already mentioned here. Yeah, just I would like to mention one point that so far we have been dealing with the NMOS transistor, but obviously current is a half mu N Cox W to VGS minus whole square. But if you use a PMOS transistor, it is a half mu P Cox WL dash to VGS minus whole square. You know that mobility of the poles is relatively less as compared to the electrons, and therefore the NMOS transistors are having better current driving capabilities, right? So whenever you would like to choose NMOS or PMOS, if you want to have a better driving capability, then you have to choose which transistors? NMOS. Good. Right. Now, one little point, because the basic building blocks I said. What are the basic building blocks? Generally, we need to have a current source, right? So this is one of the first fundamental building block which you are going to design. What is a current? If you want to suppose design a current source, you want to design a current source using a MOSFET. You want to design a current source using a MOSFET, right? Such a time just right. So a lot of things will be there, but then please tell me the time. I will stop it. Okay. So what we are now, we want to just design a current source. You want to design a pardon? I don't know. What I said is the current is a function of mobility, right? I is equal to half mu Cox W L into VGS minus with the source, right? So if this is the case, this is a if you use a PMOS transistor, it's a half mu P Cox W L dash. Mobility of the PMOS for the mobility of the holes is relatively less as compared to the electrons. So if you want to have maximum current to be larger, there is a better current driving capability. Which transistor you prefer is the question. NMOS. So right. Therefore, you can do the things using either this or that, but then you have to take a call based on whatever it is, right? Now, The fundamental building block is a current source. The question here is, can I use my saturated MOSFET as a current source or not is the question. Can I use the saturated MOSFET as a current source or not? What is a current source? For that matter, we have to answer that. You should know what is a current source. What is an ideal current source? Ideal current source. Ideal current source in the sense, as the name implies. So, it should source a current. It should source current. How? Constant current. How? Constant with respect to what? Even the voltage between the two terminals. So, you apply some voltage, right? A and B is a terminal through which there is a current source. Even the voltage across this varies, the current should be constant. Current should be constant. Therefore, x-axis is the voltage, y-axis is the current should be constant, right? So, if I want to realize it, can I use my MOSFET in the saturated region? Is the question. Obvious answer is yes, because that whatever the variation, if you neglect it, then you can use it, right? Well, therefore I can use this is the first thing, your design, therefore this is, okay, you can use indeed we use it. I have applied some negative voltage at the bulk, therefore the depletion is increased. Now the question here is, so if I apply same 0.7 volts, will the transistor be on? If I apply same 0.7 volts, will the transistor be on? Not, because the depletion is more now, right? So I have to increase the gate voltage. That earlier 0.7 volts is not sufficient now. It is more voltage I have to apply for the transistor to turn on. That means the threshold voltage, what happens to threshold voltage? Increased. So threshold voltage is going to increase, right? So far this fellow is silent, but the moment if this becomes negative with respect to source, what happened? It is actually causing the threshold voltage to vary. Therefore, you have to consider the body bias voltage also. This is called the backgate effect or body bias effect. Backgate because this is acting like a backgate, right? So by varying that also, it's just as good as now. It's as good as by varying that you are varying the threshold voltage. You are varying the threshold voltage means now it is as good as it is controlling the current also, because the current is now is a function of what? Because maximum current is it should be more and above threshold voltage only, the current increase, right? Therefore, it is indirectly controlling the current. It's a backgate effect, right? So to take that into account here, right? Therefore, the threshold voltage earlier we said we have ignored the body bias effect, and it is a function of the source to bulk, right? So that also you have to take into account. Okay. So body bias coefficient is gamma, we say. And now one small, this also I don't want. I'll try to very quickly look at this in an example of body bias. One example circuit for the body bias. We'll close it. So let me try to consider this circuit. The circuit, don't read anything here. Just look at this circuit. Okay. Let's assume that initially the bulk and the source are connected together. Initially assume that bulk and source are connected. I have not shown there. Assume that these two are connected together. Okay. Initially. Now I would like to plot V in versus V out. Okay. As V in is increasing, what should happen? As V in is increasing, what should happen? Gate to source voltage is increasing. So first of all, is there a body bias effect when these two are connected together? There is no body bias effect. When input voltage is increasing, what should happen? Gate voltage is increasing. Gate voltage increasing. Gate voltage increase, current should increase or not? When gate voltage increase, current should increase or not? Generally, don't look at all that. For a transistor, when the gate voltage is above threshold voltage, the current should increase or not? Should increase, no, it's common sense. Current should increase. So current should increase. But what I have done, I have connected a current source here. So the fixed current is flowing there. Right? It will not allow the current to increase beyond the fixed current. Right? But from one end you want to increase the gate voltage. Current to increase hona chahiye. But you are not allowing from the other end. Not allowing from the other end. Which implies that what the circuit is wise, right? It follows the rules. What it does is, कोई बात नहीं, you are increasing VG, right? Now I'll keep VG as constant. What it does? But it raises this potential. As input increases, it raises this potential so that VGS remains constant and therefore current remains constant. Because you are not allowing the current to increase, क्या करेंगे? Therefore, what it does? It is honoring. Okay, as VG increases, current should increase, all right. But it's a function of the VGS. Then what I'll do? VG increases, source voltage also increases, the VGS remains constant. So therefore, current remains constant. Am I right or not? Is it okay? So as this increases, this increases. Am I right or not? So what kind of circuit it is? What kind of circuit it is? Anupama will speak. What kind of circuit it is? You have heard about source follower, right? What source follower does? The source follows the input, right? So that is, output is following input voltage. The source follower. But for the threshold voltage, if the applied voltage is less than threshold voltage, कुछ नहीं होगा. Greater than threshold voltage, then output is simply following the input voltage variations. Output follows the input voltage variation, but for threshold voltage. Am I right or not? But for threshold voltage. All right. So therefore, if we try to plot it, it is with respect to time. If we try to plot, as input voltage is increasing, output voltage is also increasing. As input voltage is increasing, with respect to time I am plotting, output voltage is also increasing. What is the difference between these at any point of time? What is the difference? How much? What is the difference between the input and the output voltage? All the time? Constant. What is the value? Threshold voltage, right? So above threshold voltage only it conducts, right? So therefore, this is what is a source follower. Okay. Now whatever the connection we thought, we have removed it. Then what happens? So this is the source. The bulk is at ground. Source is not at ground. Therefore, the circuit experiences body bias effect. Am I right? Circuit experiences body bias effect. Okay. Now, if the input voltage is increasing, what will happen? If the input voltage is increasing, what will happen? If the input voltage is increasing, what will happen? Now, if the input voltage is increasing, I said because current is constant, this potential should rise, right? This potential should, anyhow, because this current is constant, so to keep the current constant, what it is doing? It is raising the source potential. So same thing, not you. So it is raising the source potential to keep the VGS constant. But as the source potential rises, what happens to VBS? What happens to VBS? VB is at 0 and source potential is rising now. So what happens to VBS? 0 minus S, right? So it becomes more positive or negative? Negative. So VBS becomes more negative. As input voltage is increasing, VBS becomes more negative. As VBS becomes more negative, what happens to threshold voltage? Increases. So as VBS becomes more negative, the threshold voltage keeps on increasing, right? Then to maintain the same current, I need to apply more voltage at the input. Am I right or not? Right? Therefore, we try to look at the output voltage now. The output voltage, what is happening to output voltage? As input voltage is increasing, what is happening to output voltage now? Output voltage, because I need to apply more voltage at the input to maintain the same current, then the difference is threshold voltage, right? The threshold voltage is increasing, right? Therefore, the output trails as compared to the input voltage, because just the difference is threshold voltage. Always the difference is threshold voltage. If threshold voltage is constant, it keeps on following the output, keeps on following the input voltage. But since the threshold voltage is increasing, that gap cost keeps on getting widened, right? If you use that circuit as a source follower, and if you ignore the body bias effect, then you are in soup, right? You are thinking that the output is simply following the input voltage, but it is not happening exactly because of the body bias effect, right? So here, for this body bias effect to manifest, did I apply any voltage at the bulk as I have done earlier to demonstrate that? Did I apply any explicit voltage? Did I apply any did you try to look at the circuit here? Did I apply any explicit voltage at the bulk here? It was 0 only. But then as input varies, it is showing the color. Why? Because for any voltage VAB to vary, it is not necessary that VA should vary. For VBS to vary, so the bulk is 0 only, but source is at a difference point, that keeps on changing. So therefore VBS is changing here, and therefore body bias effect is going to be there. Therefore for the body bias effect to manifest, it is not necessary that the bulk potential is explicitly varied, but then otherwise also VBS may vary if the relatively source potential varies, right. So therefore this is simple circuit, but in the big circuits here, wherever there is the source potential different from the bulk, then we have to take this into account. I will close stating one more important point, that generally in the loads for the circuits which are of course which you might have seen, the load is there. Load is a realized load is a resistor can be there, or generally load resistors are not used, active transistors are only used. The loads can be realized by what? Transistors, right. So generally we prefer PMOS transistors as the loads, right. The reason being, we don't want body bias effect, right. So why there is no body bias effect there? Because the substrate is connected to VDD there. You may ask me why substrate is connected to VDD for the PMOS transistors. Substrate for the PMOS transistors, the bulk is actually, it is N-type semiconductor, right. So we want that the bulk is N-type semiconductor, am I right or not? And the source and drain are P plus, right. There is a P-N junction there, P plus N junction. This P plus N junction should be reverse pass. Why we want it to be reverse pass? We don't want any bulk, any current to flow through the bulk. We want the current should flow only from source to drain through the channel only. But we don't want any current to flow through bulk and it gets wasted, right. Therefore, these junctions should be reverse pass. Therefore, the bulk of the PMOS transistor, which is a N-type semiconductor, is to be connected to the highest potential in the circuit, which is the VDD, right. So therefore, if you use a PMOS transistor as a load, then obviously since the bulk is connected to VDD, there is no body bias effect, right. And for the NMOS transistor, the bulk is always connected to the lowest potential in the circuit. For the same reason, we want to reverse bias that PN junction, which is P the substrate and N plus is that PN plus junction is that. Is it okay? So that closes the fundamental discussion about this, and then gradually we will try to you can just think of varying the loads of what is the amplifier, common source amplifier, what are the resistive loads or any other load, we will try to just see, and also further what is whether common source amplifier topology is sufficient, you want to go for any other topologies like cascode or whatever it is, and then this thing. Okay. So any questions at this point? Right.
Hello. Okay. I think everyone knows how to launch that CANS tool. Interesting, hello. Yeah. I think everyone is familiar how to launch the CANS tool. Okay. So in this class we are going to see inverter schematic and layout. Okay. I think everyone knows how to design an inverter. It is a CMOS inverter. You know that pull up and pull down network. Pull up is a PMOS and pull down is a NMOS. So here we will do parallelly. In your systems you can do it. I think everyone know how to launch it, how to open the schematic view and everything. So sir, close once the close tool open చేసి క్లోజ్ చేసి మొత్తం ఓపెన్ చేసి యూఎంసీ నుంచి లాంచ్ చేయి మళ్ళీ. I think everyone created the library. No? I think everyone has done the pixel. Pixel they have created one library.
In the library create inverter cell.
ఈ సిస్టమ్ యూజ్ చేసుకోండి. ఓపెన్ అయితే సో చెక్ చేసుకోండి. ఓపెన్ అయితే I think everyone has created their own library. In that they have created a cell view named pixel. So now you create a cell view naming as an inverter. Oh, yes, no. పిక్సెల్ ఎందుకు మీరు అది చేసుకుంటా అంటే ఓకే, మేము అసలు ఏం చేయలేము. ఏం చెప్తున్నాము అదేంటిది? సార్ ఏంటంటే హై లెవెల్కి వెళ్ళిపోయారు, మీకు ఏంటంటే స్టార్టింగ్ లెవెల్ నుంచి ఎలా ఉండేదని చూపిద్దామని అనుకుంటున్నాము. ఓకే, Bhaskar sir has explained about the pixel, how to design a pixel and everything he has explained. So what we are planning is to start from the inverter, to know how to make the usage of the tool. So we are interested to say inverter. If anyone interested means, today sir said no source follower. After completion of the inverter, they can try source follower. So we'll say about the inverter. You know that inverter, we have two transistors, pull up and pull down. Pull up consists of P transistor and pull down consists of N transistor. So you take the two transistors PMOS and NMOS. Already you have created a library, no? Library tools, library manager. There you can find the library. మీరు ఆ సిస్టంలో చేశారు కదా మొన్న. మీరు లైబ్రరీ నేమ్ ఏమి ఇచ్చారు అక్కడ? ప్రీవియస్గా పిక్సెల్ చేసేప్పుడు నేను చేసి చేసుకోండి మరి. ఆల్రెడీ లైబ్రరీ ఉంది కదా, మనం మీరు చేశారు కదా, మరి అక్కడ కూర్చోవచ్చు కదా, అక్కడైతే సరే క్రియేట్ చేయండి, లైబ్రరీ క్రియేట్ చేసుకోండి మళ్ళీ. ఓకే, లైబ్రరీ క్రియేట్ ఏ సెల్ వ్యూ. సెల్ వ్యూ హ్యాస్ ఇన్వర్టర్. సెల్ వ్యూ హ్యాస్ ఏ ఇన్వర్టర్. ఫైల్ న్యూ సెల్ వ్యూ. టెక్నాలజీ ఇంకా యాడ్ చేయాలి. ఏం పేరు ఇచ్చారు? ఇక్కడ ఇన్వర్టర్. ఓకేనా సార్? I think everyone knows how to call instance from the schematic. For connection, go for W. wiring. ఏమవుతుంది ఇది ల్యాండ్ డిసేబుల్ చేశారు మళ్ళీ ఒకసారి ల్యాండ్ కనెక్ట్ అవ్వాలి రాజు విధానం దీంట్లో ఇన్వర్టర్ క్రియేట్ చేసుకున్నాం ఓకేనా సోర్స్ ఇన్స్టాల్ ఫీచర్స్ దీంట్లో మీరు ఆల్రెడీ క్రియేట్ చేశారు కదా ఒక లైబ్రరీ దాంట్లో సెల్ వ్యూలో టూల్స్ లైబ్రరీ ఓకే in the morning section sir has said that pull up p transistors the bulk connection has to given to the source terminal higher potential and n type has to given to the lower potential. So here we have given the p type has higher potential which is connected to morning section sir has said no PMOS body connection has to give positive higher potential and NMOS has to give lower potential. In this way you have connected with the body connection. Okay. సార్ ఒకసారి ఎస్కే కొట్టిన డబ్ల్యూ కొట్టి దాన్ని క్లిక్ చేయండి చాలు క్లిక్ చేసి మూవ్ చేయొచ్చు మీరు ఎలా పట్టుకున్న దగ్గర ఒక రెక్టాంగిల్ వచ్చింది అది ఎలా క్లిక్ చేసి ఒకసారి అడగాలంటే అటు చెప్పుకోవచ్చు ఎక్కడ మనకి బెండ్ కావాలంటే అక్కడ సింబల్ చేద్దాం మేడం everyone completed up to here you need to take instance from UMC వచ్చినాయా NMOS 18 PMOS 18 రొటేట్ ఎందుకు కనెక్షన్ ఇచ్చేసండి కొట్టండి ఏమవుతుంది ఇప్పుడు N33 కాదు everyone take the transistors as N18 mm don't take 33 N33 don't take go for N_18 what Bhaskar sir said that is a pixel he designed with using 33 మనం దానికి ఆల్రెడీ చేసినాం కూడా మనం now everyone look at on the screen once who are not created the circuit once look at this everyone This is the window you are going to see before after opening the tool. This is the CAW window. In here you need to go for tools. I think everyone created the library. Everyone created the library. So go to tools. Tools you can find library manager. Okay. In library manager you need to see what is the library that you have created. Okay. You can see your library. Okay. In the same way, then you need to go file. Here it is a file corner. There new. You need to go to cell view. File, new, cell view. Click on that. You will get a window. Here the library name is the name which you created. It has to be there. And the cell view is the inverter. View type, schematic. It has to be there. Okay. Up to here, no doubt. Okay. Then press OK. You will get a window, schematic window. Here you can see schematic editor L. Your directory name will be here. And inverter. Okay. Here you need to call the instance. So here is an option. Instance. There you need to select. Library name is UMC. The technology we are using UMC 180 nanometers. So it is UMC 18 CMOS technology. So in here you need to select the library and the cell view. Cell is a P_18_mm. You need to take P18. Don't go for P33. Take P18. Okay. P18. And view symbol. And next hide. You get a P type. In the same way, go to instance. Now you need to select N18. N18 underscore. Okay. Adamotunda. Everyone has completed up to here, no? Okay, now. After that we need connection W, wire. You just click right button once click on that wire and you drag it. It is inverter. Inverter we know that CMOS. Both P type and NMOS will be shorted, which is giving us input. It is a pull-up transistor is a P transistor, and the bulk connection has to go for VDD. And pull down, it is a N transistor, its bulk connection has to go to 0 potential. Now add the pins. Okay. Just to zoom out that schematic, you can press F for fit. It will fit to the window. If you press F, it will fit to the window. Okay. Now you have to create the pins, because we need to create a test bench. So go for pins P, or you can find here option P. Pins, you know that input pin, VDD pin, output pin and ground pin. 4 pins has to be there. Create pin, you can give names at a time by giving some space. VDD, input, output and ground. And here is the direction we can see, no? We recommend to take input or output direction. It is a bidirectional pin. If you take only input means it will sometimes it may vary. So to take better input and output direction pin. It can be acted on bidirectional pin. So take a directional input and output. ఇన్పుట్ ఇచ్చాము అవుట్పుట్ ఇచ్చేస్తున్నాం అనుకోండి సార్, నెక్స్ట్ దానికి ఒకవేళ ఇన్పుట్ అయింది అనుకోండి, అక్కడ పిన్ ఎర్రర్ వస్తుంది. ఇప్పుడు ఒకవేళ బఫర్ డిజైన్ చేస్తున్నాం అనుకోండి, ఇన్వర్టర్ 2 ఇన్వర్టర్స్ కావాలి కదా, ఈ ఇన్పుట్ దానికి అవుట్పుట్ వస్తుంది కదా, అప్పుడు వేరియేషన్ వస్తుంది. సో బెటర్ టు టేక్ ఇన్పుట్ అండ్ అవుట్పుట్. సో place the pins where we needed. Here VDD, input, ground pin, output. Fit chain banega. Okay. Okay, I'm going. While schematic akkala chesaru. కనెక్షన్ ఇచ్చేసాం. ఏమవుతుంది? ఇన్పుట్ గ్రౌండ్ ఎస్కేప్ కొట్టేసి పిన్ కొట్టు పి వచ్చేసి ఆల్రెడీ ఇచ్చేసావు కదా వీడి పిన్ ఇన్పుట్ గ్రౌండ్ స్పేస్ గ్రౌండ్. After placing the pins, check and save. Here is an option. Here you can find check and save option. If you check and save, there will be no errors. It means it properly connected. Okay. ఇది ఒకటి ఆచరణ చెప్తారంట. Completed. Check and save, no errors. Okay. Now the schematic is completed. Now we need to run this schematic. So for this we need to create a test bench. So if we create a test bench means we can add sources directly to this one. Everyone completed up to here? Any errors? No errors? Connections connected properly. Gian ఇచ్చేసి ఎఫ్ అయిపోయిందా బై డైరెక్షన్ తీసుకో ఇన్పుట్ అవుట్పుట్ కావలేదు మేడం okay. Everyone created the schematic now. Now we need to create a symbol. Here we need to go for create cell view. From cell view press OK. Here we have the pins VDD. What are the pins that we have given in the schematic will reflect here. VDD, V in, ground and out. The placement of pins can be placed as usual. We have taken bottom as a ground, on top as VDD, left as out and right as in. Placement of pins base lift, because based on your necessary you can take. Left as in, right as out. Okay. VDD small a, GND. Then press OK. You will get another window which is we created a symbol. Modify చేద్దాం అవసరమా మోడిఫికేషన్ ఓకే పెద్ద చేయి స్క్రీన్ పెద్ద చేయి F కొట్టు you will get a symbol like this. So you know that inverter symbol is not like this, so we need to edit that one inverter symbol. So for that one you delete this layer, these two layers. Don't delete the pins, delete only these two layers which is showing the red color and the green one. Don't delete the pins. port name inverter port name. Here you can write inverter port name. You click on that, you will get your option T text. Or double click on that one, you will get. You double click on that one, you can edit that one. Inverter. Any doubt? Pins రాట్లేదా? ఎర్రర్స్ వచ్చినాయంటే నువ్వు కనెక్షన్ సరిగా ఇవ్వలేదని అర్థం. ఇక్కడ కనెక్షన్ వల్ల అవ్వలేదు, అది ప్రాబ్లం. ఒక్కసారి కొద్దిగా ఇక్కడ నువ్వు కనెక్షన్ సరిగా ఇవ్వాలి, అది ఎర్రర్. ఇక్కడ మధ్యలో ఆపేసావు కనెక్షన్ ఏంటంటే పూర్తిగా కంప్లీట్ చేయాలి. ఇప్పుడు చెప్పని సేవ్ చేసి 2 9. Okay, symbol, create cell view. You can use F option for fit. To fit the window, you can use option F. పిన్స్ పెట్టేసుకోండి. Here we need to draw the inverter symbol, so we go for wire. Here is a symbol, we need to do some artwork. You select that wire, you can see a line, you can select that one and you can drag that. Double click them, you double click on that, escape, and double click, enter inverter, enter చేయబోతుంది, enter inverter. ఒక నిమిషం ఎస్కేప్ కొట్టండి, ఎస్కేప్, డిలీట్ ద వన్, దిస్ డిలీట్, ఇదే ఆప్షన్ డిలీట్, సెలెక్ట్ దట్ ఇన్స్టెన్స్ నేమ్, యాడ్ ఇన్వర్టర్ దే, టెక్స్ట్ టీ, one second, it's not coming way. ఒక నిమిషం, first let's just delete this, green line and the green line one. Now escape, now double click on that one, escape, double click, కొద్దిగా ఫిట్ చేసుకోండి. ఓకే ఒక నిమిషం ఇక్కడ ఉంది కదా ఆప్షన్ ఓకే ఈ పాయింట్స్ ఇక్కడ మూవ్ చేసుకోండి ఆప్షన్ ఇవ్వము ఇక్కడెక్కడొక్కడు ఓవర్లాప్ ಸ್ವಲ್ಪ ఓకేనా అలా ఇది కూడా మొత్తం సెలెక్ట్ చేసుకొని ఆప్షన్ ఎక్కడైనా పెట్టేసేయచ్చు నెక్స్ట్ సర్కిల్ ఓకే నేను ఓవర్లాప్ అవ్వాలి సార్ ఈ లైన్ కరెక్ట్గా సెట్ అవ్వాలి మొత్తం కాపీ చేసుకోండి చికెన్ సార్ తీసుకొచ్చి దాని మీద పెట్టేసాయి మొత్తం కాపీ చేద్దాం దాని జోలు వైర్ ఒకసారి క్లిక్ చేసి డ్రాగ్ చేయండి వన్స్ క్లిక్ దేర్ ఎండ్ పాయింట్ ఎఫ్ కొట్టు ఎఫ్ వైర్ తీసుకో వైర్ పక్క లైన్ ఎక్కడ కావాలంటే డ్రైవ్ చేసుకో అలా తీసుకొచ్చేసి ఇక్కడ తీసుకొచ్చేసి ఇది లాంగ్ డిస్టెన్స్ అలా తీసుకెళ్ళి సెలెక్ట్ ఎవ్రీథింగ్ మొత్తం సెలెక్ట్ చేసి దానికి యాడ్ చేయండి చెక్ అండ్ సేవ్ నౌ చెక్ అండ్ సేవ్ if you check and save means you should not get any error వచ్చిందా సార్ it's not a problem if it's overlap also it's not a problem pin because it is just a symbol కొద్ది దూరం తీసుకొచ్చి ఒక నిమిషం చదివి ఎస్కేప్ సి కాపీ మొత్తం కాపీ చేసుకొని జమ్ అలా అన్ని ఇలా యాడ్ చేసుకొని దీనికి యాడ్ చేయండి ఈ లైన్ తీసుకొచ్చి దీనికి యాడ్ చేయండి సి కొట్టేసి కాపీ చేసుకొని ఎస్కేప్ కొట్టేసి మళ్ళీ ఎవ్రీ టైం ఎస్కేప్ మొత్తం సెలెక్ట్ చేసుకో ఫస్ట్ అన్నీ సెలెక్ట్ చేసుకోవాలి మొత్తం ఫస్ట్ ఏం చేస్తాం ఎస్కేప్ కొట్టేసి మొత్తం సెలెక్ట్ చేసుకో డ్రాగ్ చేసుకోండి సెలెక్ట్ చేస్తారు కదా ఫస్ట్ మౌస్తో సెలెక్ట్ చేసుకోవాలి ఏం మూవ్ చేయలేము కాపీ లేకపోతే మూవ్ మళ్ళీ ఎస్కేప్ సేమ్ ఇది కూడా అంతే symbol is created, no? Totally select చేసుకుంటాడు. ఫస్ట్ సెలెక్ట్ ఎవరిది అలా పిన్నాను కదా, ఫస్ట్ ఇలా సెలెక్ట్ చేసుకోండి. ఎం మూవ్ చేస్తే తర్వాత ఎస్కేప్ కొట్టండి. వీటికి రాను ఏం కదా, జస్ట్ లేబుల్ అంతకంటే ఇంకొద్ది పైకి తీసుకోవచ్చు. ఇట్స్ నాట్ ఏ ప్రాబ్లం, జస్ట్ ఇది అలా పెట్టేసుకో, అదే ప్రాబ్లం. అయిపోయిందా? రాలేదా? ఇన్వర్టర్ అయ్యని ఇచ్చేసి చాలు. ఆల్రెడీ చేసాం కదా, మళ్ళీ చేస్తున్నారు. I think everyone created the symbol and check and save now. Okay, over now. That's one. What's what up to check and save? Check and save. Check and save. Now close this window. Again here. Here again you go for the file. Now you need to create a test bench. The schematic which we created, we need to run this one. For this one we need to create a test bench. For that we need to go for new as it is, which we created the schematic inverter. No, there you need to go for inverter underscore test bench TV. Same file, new, cell view. Here inverter TV schematic. You will get another pop-up window, schematic window. Now we created the symbol. For that one we need to create a test bench to see how the inverter is going to operate. I think everyone got the new window, no? Okay, okay. Underscore TB to identify it is a test bench. Now here we call the instance, no? We have added the instance, no? Here we clicked and we have added the instance. You need to select this one, add instance. Here library. Here the library which you created a library name, no? You go to in that library, the library which you created, you select your library there, because the schematic which we designed is in our library, so we need to call that symbol to here. Okay, and the cell view is the inverter. Cell view is the inverter, or the name which you gain for creating the symbol. No, inverter నాకు schematic ఏం చేశారు? లేవు. సెల్ వ్యూలో ఏం చేసావు? ఇన్వర్టర్ ఇందాక చేసావు, సెలెక్ట్ చేసుకో. సెల్ వ్యూ ఆల్రెడీ ఇన్వర్టర్ ఉంది దాంట్లో, ఒకసారి క్లిక్ చేయి. ఇన్వర్టర్ ఫస్ట్ symbol. Now you will get an inverter symbol like this, which you created the symbol. Schematic lo modify చేసా, సేవ్ చేయలేదంట మరి. బ్రాకెట్స్ ఇచ్చావు ఏంటి ఎక్కడన్నా బ్రాకెట్స్ తీసేయాలి మొత్తం తీసేసి ఇన్వర్టర్ ఏం చేసావు ఎర్ర ఎందుకు వస్తుంది చికెన్ సేవ్ చేసావా సో చికెన్ సేవ్ వస్తే అక్కడే నువ్వు సాల్వ్ చేయాలి దాన్ని ఇక్కడ తీసుకొస్తే సేమ్ ఎర్రర్ వస్తుంది అదే చెప్పింది కదా ఇక్కడ ఇది లేఅవుట్ని క్రియేట్ చేసినట్టున్నారు కదా ఇక్కడ అది ఓపెన్ చేయండి లేఅవుట్లో మీ స్కీమాటిక్ సింబల్ ఓపెన్ చేయండి నో లైబ్రరీ ఈజ్ యువర్ లైబ్రరీ టాప్ the library which you created down open the symbol double click open it now check and save no what the name that you have given one name no inverter you call that one ఏమవుతుంది మళ్ళీ క్రియేట్ చేయండి ఎర్రర్ వస్తుంది నీ ఇష్టం అదే ఉంది ఇలాగే వచ్చింది సార్ ఇన్వర్టర్ ఇప్పుడే కదా దానికి సోర్స్ క్రియేట్ చేయాలి ఇన్వర్టర్ సోర్సెస్ చెప్పమంటారా రాకేష్ ఇన్వర్టర్ సోర్సెస్ కనెక్ట్ చేయి now we need to connect the sources so instance I here we need to add the sources we can find the sources only from nlog library the library in library you need to select nlog library same instance nlog input pulse kada v pulse ఏది ఉండదుగా v pulse కదా ఒక అయితే స్నాక్స్ వచ్చింది v pulse చూడు v pulse na here cell v we need to select v pulse because the inverter we need to go the pulse signal v pulse v pulse కదా v pulse వచ్చిందా v pulse ఏమవుతుంది సరే నువ్వు ప్రొసీజర్ రాసుకోండి తర్వాత చెప్తాము ప్రొసీజర్ రాసుకోండి ఎర్రర్ వస్తుందా వస్తుంది స్కీమాటిక్ ఏమంటారు ఇది సింబల్ డిలీట్ చేశారా ఓకే చూద్దాం అందరూ ప్రొసీజర్ చూసుకోండి మళ్ళీ ఇన్వర్టర్ సింబల్ డిలీట్ చేసుకుంటుంది టెస్ట్ బెంచ్ క్రియేట్ చేసుకుంటుంది మళ్ళీ వచ్చింది నౌ వి నీడ్ టు యాడ్ ద v pulse and now we need to hide okay now we will get a pulse and supply voltage we need to go VDC అక్కడ ఇచ్చేసి take instance I analog library, and you need to give VDC. Two sources has to be there. One is VDC, one is vpulse. VDC and vpulse. DC is the which is used to give power supply to the inverter, and pulse is the input signal. VDC. After that, connect VDC and pulse. మళ్ళీ మీరు అది డిలీట్ చేసి ట్రాన్సిస్టర్ కంచి డిలీట్ చేసి ఉంటాను. గ్రౌండ్ కూడా ఇచ్చేసి after connecting you can give ground analog library. In the same way you can find analog library G and D. ఆల్రెడీ ఉంది కదా ఇన్వర్టర్, దాంట్లో చేసేసండి. ఇదే ఓపెన్ చేసి దాంట్లో ఇన్స్టెన్స్ నుంచి కాల్ చేసుకోండి. అండ్ V pulse, we have to give the pulse. You need to select the pulse. అయిపోయిందా? అవ్వలేదా కొంతమంది? And we need to give the output pin. So select P, or you can go here P and give the pin output out. Ground out. After that, check and save. సింబల్ కాల్ చేసుకున్నావా? అందుకే ఈ ప్రాసెస్లో ఉన్నప్పుడు చెప్పుకుంటే చూసుకున్నాను చెప్పేది. సేవ్ చేసావా? ఒక డిస్టర్బెన్స్ క్రియేట్ చేసుకోవాలి. ఇంట్లోకి ఇన్స్టెన్స్ నుంచి మీదేంటిది ఈ సింబల్ కాల్ చేసుకోవాలి. ఇక్కడ ఎన్లాగ్ లిబ్నెస్ నుంచి V pulse తీసుకోవాలి. VDC resource. This వెళ్ళొద్దామంటే వెళ్దాం సార్, వెళ్దామా?
ఇంకా రాలేదు నాకు కూడా
టీ బ్రేక్ ఇస్తుందా? టీ బ్రేక్ ఏమంటారు సార్? టీ బ్రేక్ అప్ టు హియర్ ఎవరైనా కంప్లీట్ హూ హాస్ కంప్లీటెడ్ కెన్ గో ఫర్ టీ. స్మాల్ బ్రేక్. You can have a small break outside.
ఛార్జ్ చేయలేదు కదా ఇది ఉంటుందా ఛార్జ్ చేయకపోతే చాలదే So morning we have seen morning so we have seen that by varying VDS actually the length of the channel is being varied, so we call this as a channel length modulation. The length of the channel is being varied with the VDS, therefore channel length modulation. ఏమైంది ఇప్పుడు ఎగరడం మొదలెట్టిందా పొద్దున బాగానే ఉంది so పొద్దున బాగానే ఉంది So the actual length is L dash and then original length is L and then there is a change is L delta L. So therefore L dash is equal to L minus delta L. L dash is equal to L minus delta L and so if you try to take 1 by L dash then it is I can write it as so L dash is equal to L minus delta L, 1 by L dash is equal to 1 by L minus delta L. So 1 by L into 1 minus delta L by L. So delta L by L is very very small. We said that delta L is small as compared to L. Therefore, if you call this X here, when X is very small, 1 by X, 1 minus X whole to the power of minus 1 can be approximated by a binomial expansion, right? 1 minus X whole to the power of minus 1 can be written as 1 plus X minus X square by 2 and so on, right? Therefore, it is just approximately all higher order terms I can neglect. It is simply 1 plus delta L by L, right? So this is 1 by L into 1 plus delta L by L. So let me try to substitute that value here. Okay. So in the current expression, right? So this L dash, I'll try to write it as, this is 1 by L dash is equal to this, right? Okay. So this is actually 1 by L dash is equal to what it is? 1 by L into 1 plus delta L by L. So I'll replace 1 by L dash as 1 by L into 1 plus delta L by L. This delta L by L, I'll write it as lambda VDS, the function of the VDS, right? So this is now 1 plus lambda VDS, okay? Therefore current is expressed as ID is equal to half mu C of W by L into VGS minus V the whole square into 1 plus lambda VDS. Is it okay? ఇంతకు బాగానే వచ్చింది, ఏమైంది ఇప్పుడు? తీసిపెట్టండి అంతే, తీయండి పెట్టండి. అంత ఊపుతారు దానికి, అంత ఊపుతూ తీస్తారు ఎందుకు? So whenever TV cable is not coming, when he says help, you try to ring, then first you remove the connection and connect it again and check it, right? So exactly same. Huh? So all right. So if you go to doctor and say that no, my eyes are not properly visible, remove it and then you can come it. Okay. So the transconductance, now what we have done is we have actually evaluated current by taking into account the channel modulation effect. Actually what I said earlier is current is equal to half mu Cxw by L dash into Vgs minus V whole square. L dash is actually length is varying. It is a function of the VDS, but then VDS is not visible there. So what is there in your hand is VDS is varying, but length you cannot go inside the MOSFET and verify how much length it has varied. So therefore what you have to do, is, because what you know is only the VDS. I am varying VDS, current is varying. You just express as L dash, I can't do because I don't know what is L dash. Therefore I should express it in known parameter. What known parameter? VDS, which I am changing. So therefore I express ID in terms of the known parameter, right? That's a lambda VDS, right? This is called channel length modulation coefficient lambda, right? All right. So similarly, once you know that current, then again dou ID by dou VGS you try to do and evaluate the GM accordingly. Okay. Now so far we thought that by when the applied voltage, gate voltage is less than the threshold voltage, the transistor is off actually. We are thinking, but in the beginning I said that for a given gate voltage, at least some of the electrons keep on traveling. Therefore, some amount of electrons will be there, and therefore there is a possibility of current. However small it is. So therefore, such current we call it sub-threshold conduction. When the applied gate voltage is less than threshold voltage, we call it sub-threshold. And if we try to model it, we will not go into the details, but then it is behaving in the exponential fashion. So therefore, the current ID is equal to I naught e power VGS by KT by Q. Okay. So we will not deal much about this, but one thing I can say that in the sub-threshold conduction also you can just use where the sub-threshold conduction will be useful is the question here. So if we try to look into actually very quickly look at the transconductance GM. So transconductance in the saturation. Transconductance is a mu C ox W into VGS minus V threshold. And by looking at this, I want actually what I said, the larger the GM, the better it is, right? Because better sensitivity, gain is GM or not, therefore I will get better gain, therefore I want to increase the GM. If I want to increase the GM, then what is the immediate thing that, I will try to increase W by L. So probably I will go for larger GM. So if we try to increase W by L, then what is going to happen? If we increase W by L, what is the problem? If we increase W by L, right? The W increases by keeping ID constant. Then I want to keep ID constant, but I want to increase W by L, right? So I want to increase W by L, but I want to keep ID constant. So try to look at the ID expression. ID is equal to half mu C ox W by L into VGS minus V whole square, right? So I want to increase W by L because I want to increase GM, right? but I want to keep the bias current to be same because power dissipation I don't want. So if I try to do that, then what should I do? What is the other variable? ID is equal to half mu Cox W into VGS minus V threshold square. W I am increasing, I am keeping ID constant. Therefore, this VGS minus V threshold should decrease, right? So when V threshold is constant, so when I try to decrease VGS, then this fellow may try to approach V threshold, right? And if I try to further do it, it may go below V threshold, right? When they enter goes below V threshold, then it is a sub-threshold conduction. That is a sub-threshold conduction, right? So this implies in MOSFET, what happens is the device enters into the sub-threshold conduction, right? So therefore, what the bottom line here is that if you want to get larger transconductance, you try to increase W by L, all right? But then for the same ID, the device enters into the sub-threshold conduction. Even then you are happy, chalo, to kya hai? But the problem is, here what you are doing, you are increasing W by L, therefore the larger the W, the larger the size, the parasitic capacitance is more, and therefore RC time constant is more, which implies that it takes more time to charge and discharge to affect the changes. So therefore speed is at stake. Therefore you are thinking here, I am happy that I am getting larger gain, but the question here is the speed is very minimal. So these are the pros and cons about the sub-threshold conduction. Therefore definitely we will go for sub-threshold conduction, but the question when you are going to operate particularly under very low voltages, maybe energy harvesting, all these things, there we operate the transient sub-threshold, but we have to see the speed is at stake. If you want to larger speeds, probably it is difficult. So then this is the layout and all which you have been doing. Just I will not focus much about since I have some certain agenda I want to cover. Therefore, let us try to quickly move on. So the capacitance, MOSFET capacitance, very quickly try to look at the capacitances. Wherever there are two metal-like things which are separated by dielectric, then there exists capacitance, right? So here you can see there, this is the gate and this is the drain. So there will be CGD. This is the gate and this is source. There will be CGS, and therefore similarly all many capacitances are there, right? So because of these capacitances now, also there will be, you can see there is overlap capacitance here, and there is overlap capacitance here. So this is the overlap area, gate and source, gate and drain overlap area. So there is overlap capacitance, right? So you have to take into account all these all these capacitances when you are actually dealing with the circuit. Okay. So here you have to see the capacitance broadly can be thought of two types. One is oxide capacitance, another one is junction capacitance. Basically based on what is the insulation between the two plates. The insulation is oxide, then we say it is oxide, otherwise it is junction capacitance, right? So and the oxide related capacitance is basically the two overlap capacitances are fixed here. That is whatever the gate and drain, gate and the source, they are fixed here. The value is Cox multiplied by W into length is the overlap length. Okay, and so gate channel capacitance. Next one is gate channel capacitance. So the gate to bulk capacitance in the cutoff region CGB, but with the gate and bulk, in the cutoff there is no channel at all. So between the gate and the bulk, so the capacitance is CGB. Okay, CGB. So this gate to bulk capacitance is the Cox into W into L. Okay, and in the linear or the saturation region, there exists channel. There exists channel here, right? When the channel exists here, in the linear region, we can assume that this is more or less is a channel exists uniformly almost there. So what we can do is this channel we refer it as we refer to both the source. See, the capacitance is between gate and the channel. The capacitance between gate and channel. But once again the same story. Gate and channel means how do you effectively measure it? Channel के अंदर घुसकर तो हम तो नाप नहीं कर सकते हैं, right? Therefore, what you have to do, it should be referred to the two terminals, which is a source and drain. So when in the linear region the channel is existing uniformly along the length, and therefore we refer it equally to both the source and the drain. So therefore half into Cox into W into L for both the source and drain we refer. But in the saturation region it is not the case, because at the drain, the saturation region at the drain there is no channel at all, right? So therefore it CGD between the gate and the drain is 0, right? Only we refer to the gate and source, and it is 2/3 of the Cox into W into L. So this is what is the capacitance. Okay. So therefore we can just tabulate it in such a way that, so here for the cutoff region, this is CGB is Cox into W into L, and the linear region, of course, because there is no more current to the bulk here, therefore they both are 0. And CGD is Cox into W into LD all the time, for every time throughout this will be there, because overlap is always constant here, and this is overlap is all the time there, plus half into Cox into L for linear region. For the saturation region, it will be, where is saturation? Yeah, saturation. For the saturation region, this will be 0, right? So this is Cox into W into LD. What is this? CGD. Okay, CGD is this one. And what is CGS here? CGS in the linear region, half Cox WL plus Cox W into LD, and CGS is 2/3 Cox W into L plus Cox W into LD. Is it okay? So there's no big deal here. One thing you have to remember is the gate to channel capacitance is referred to source and drain, whose value is half into Cox into W into L for both gate source and gate drain. And for the saturation region, it is gate and drain, it is 0, gate and source it is 2/3 of Cox W into L. Alright, so let's move ahead, and not only that, there will be sidewall capacitance also will be there, sidewall capacitance also will be there. So these are various channels are there, various junctions are there. So this is the first junction is what is N plus, this is N plus here, and this is P, N plus P junction. And second one is this is N plus and this is P, the N plus, the second one is N plus and P plus, because all the three sides we try to put channel channel stop implantation will be there. We try to clad with the P plus all the three sides, so that unnecessarily there will not be any current flowing to the adjacent MOSFET. So therefore through all the three sides there will be P plus channel stop implantation. So therefore here all the three sides external to the substrate, there will be what called P plus implantation. Therefore this is here this side it is N plus and this side it is P plus, N plus P plus junction. And whereas this one is also N plus P plus junction, right? And how about this fourth one? Fourth one is also, this is N plus and this side it is P plus, right? And the fifth one is bottom plate. Bottom plate is, this is N plus and this, below this what is there? It is substrate P. So therefore it is N plus P junction, N plus P junction. So these are the various junctions, because whenever there is P junction, basically based on the doping and all, the corresponding P junctions you have to take into account, right? So this all I just to mention. I will not go much into details of that. Okay. So now we will try to we'll quickly move into small signal model. Okay, the small signal model, let's try to just look at it is how do we model the MOSFET here? It's by varying the gate voltage, current is varying. By varying the gate voltage, current is varying. So how can I view it? It is just like a voltage dependent current source. It's giving me almost, see in the saturation we are thinking that current is constant, ignoring the channel the modulation. So it is a current source. Which type of current source it is? Voltage dependent current source, because by varying the gate voltage, it is voltage dependent current source. So therefore it is represented by voltage dependent current source. And what is it? GM VGS. Why? Because the current is varying. It is dou ID by dou VGS is GM. So therefore the magnitude of the current is GM VGS, right? Dou ID by dou VGS into VGS is ID, right? Therefore GM VGS. And then this is the gate, this is the source, therefore I am applying voltage here VGS. This is small signal model. Okay. Now what is R0 for this? So if you want to evaluate R0, dou VDS by dou ID, I want to evaluate. Dou VDS by dou ID is 1 by dou ID by dou VDS. I know current expression, try to just using the channel the modulation and all. So do that, simply you will get 1 by lambda. If you do that, you will get it. I am not spending time here. 1 by lambda, ID is the resistance. Okay. So now, but I have to take that also into account. Because in this case we are ignoring the channeling the modulation. So by the virtue of channeling the modulation, if you ignore the channeling the modulation, R naught is infinite because dou ID by dou VDS is, there is no change in delta in the current with respect to VDS. Therefore, dou ID by dou VDS is infinite. The delta ID is 0 with respect to VDS, right? So therefore, dou VDS by dou ID is infinite. Dou ID by dou VDS is 0. Dou VDS by dou ID is infinite. R naught is dou VDS by dou ID, which is dou VDS by dou ID is infinite. So we are not, I am not putting anything here. But then, there is a change by the virtue of channel length modulation. So therefore, I have to represent that also as a function of. So how do I represent? It's just like alpha VDS or whatever. So I can replace also another voltage dependent current source, but then to make our life easier, we'll replace this with a resistance because the slope, that variation not that much. Therefore, I can say just like a resistance. So that variation I will replace it by value R naught. I will replace it by R naught, whose value is 1 by lambda ID. Okay. So therefore, equivalent. So in the other one is there we ignored the bulk effect. So current is also varying with respect to VBS. That is another voltage dependent current source. Another voltage dependent current source, dou ID by dou VBS. That also you have to take into account. Therefore, dou ID by dou VBS you have to just calculate it here. This is current expression, but then where it varies actually the threshold voltage, right? Because threshold voltage varies with respect to VBS. We have seen that, right? So I just now do a little bit of math, then say I will get GMB as this one. Okay. So finally, your responsible equivalent circuit is just like this. So what you can see here is this is a voltage dependent current of GMVGS, R naught due to channel length modulation, GMB VGS towards the body bias effect, because current is also a function of VBS. Okay. Well, this is the final responsible equivalent circuit. Okay. So let us try to move very quickly. This is actually capacitance varies. Let us try to, I am eager to move towards it, but then let us try to, we want. Okay. So how do we see MOSFET as a capacitor? How do we see MOSFET as a capacitor? Very quickly let us try to look at how to view the MOSFET as a capacitor. So capacitor is a two-terminal device, right? So MOSFET we have 3 terminals. What we will do, the source, drain, bulk of the MOSFET are grounded here, right? Source, drain, bulk, तीनों को ground. What is left over? So it is now between the gate and ground. That's all, right? So gate is there, and all the other 3 terminals are other terminal, 1 terminal. So there are the 2 terminals. One is gate, other one is all the 3 terminals put together. Now it is a 2-terminal device. It's a 2-terminal device, right? So what is there in between? In between, silicon dioxide is there. Therefore, some insulator is there. I can view it as a capacitor, right? Because polysilicon is a metal-like, and then below it is a semiconductor, and then in between what is there? Silicon dioxide, right? Therefore, let's say to sometimes when you want to analyze for very deeply, then you have to put double jet. So and later way. Okay. So transistor therefore can be considered as a 2-terminal device. Okay. So what you are doing initially, I will try to put vary the gate voltage with a negative voltage. So the gate voltage is very negatively, right? When VG is less than 0. When VG is less than 0, then what happens here? The less than 0 negative voltage is applied, right? So all the holes get attracted towards, holes are getting attracted towards the oxide silicon, right? So therefore this is called accumulation region. This is called accumulation region. Okay. So now as VGS rises, what happens? As VGS rises, the density of the holes at the interface is going to fall. So as VGS is going to rise, what is going to happen? So the holes, because now I am making it more, first it's negative I said, so holes have come up. Now gradually from negative, gradually it is coming towards 0 and it is becoming positive. What happens? The holes get repelled. The holes get repelled. Gradually the amount of the holes first reduces, accumulation to khatam ho jayega, right? And then what happens? Depletion region forms, right? So therefore the device enters into the weak inversion first. Okay. So as gradually all the holes have gone, then what happens to capacitance here? You know that capacitance is epsilon naught A by D. D is Tox separation. So what happened earlier? So only Tox is the separation. Only Tox is the separation. Epsilon naught A by this is the distance Tox, right? Oxide thickness. I got some capacitance value. Now what is happening? As I am making this gradually from negative towards positive, these accumulated holes have gone, right? But then what happens? It causes a depletion region will be formed. So depletion region, hey, this is crying. It needs charge. Behind mobile acceptor as mobile acceptor. Now what the effective separation between and metal. What is this? So in the increase, what happens? So right, therefore, so therefore the capacitance keeps on, right? But the moment the applied voltage is greater than sold voltage, then what happens? The depletion earlier holes are there, electrons go on later. Therefore, that is a complete question. Now what happens again? What is happening capacitance? So that's what. So the capacitance now we can see that MOSFET is capacitor and have a capacitance of high value using a largely now what I am ID current is a by definition here, I can write dou IT by dou and dou write the current. Now what I can, but I know it is current start right. It is equal. So is equal. Whatever the current I put. So, what value the gain? Gain is equal to and so I can write so this is C. Current is obviously. So we always see that that's good. So now if you want to evaluate on the remote. Value the gain. So which case what we do? So this is all three modes ready. Not so not is equal and not and similarly current bias mode. So how calculation is expressed bias mode current bias the current voltage bias mode given is there is the case for the when you do that the current bias find the gain. So, so what we will do set up a case in what we have done. So far we have forward. Case. Okay. What those capacitances here? Capacitances are different sources. Here are this. Big KCL. KCL log. So this is a time divided by 1 by the that becomes a K minus and the leaving current here and what is the other condition V naught divided by R naught V naught divided by. So all if you solve. So you can also verify that at zero frequency SC is equal to j omega, right? So omega is 0, simply this all will go and minus GM or not, right? So I can write my gain as the in terms of C total, this is what is the gain here, and that is a naught into the GM naught is a naught. I have put here. I will try to express this way. Okay. Now what I would like to just make an assumption is that this omega CGD is far for the frequencies omega CGD by GM is far less than 1, right. It is not a, I am not doing any violation here. What I am trying to do is omega CGD by GM is far less than 1. That is what I am just because GM is pretty larger generally. GM is larger, and I am trying to consider those frequencies for which omega into CGD by GM is far less than 1. Generally it is the case, whatever is because I said GM is pretty large, and CGD is of the order of the femtofarads, already of the order of femtofarads, and divided by large GM try to put here. Therefore I try to get here that value will definitely be small, far less than 1. So I can just now ignore for those frequencies, and then this is approximately equal to this here. So therefore gain bandwidth, this is the gain here, and the gain bandwidth product if you want to evaluate, because this is the gain, and this multiplied by gain bandwidth product, right. So before we go to that, please try to see that this describes the frequency response of a system with one dominant pole. There is only one dominant pole. What is that pole here? The pole is if you want to evaluate omega is equal to 1 by R naught C total, right, 1 by 2 by R naught C total, right. So therefore the bandwidth is given by 1 by R naught C total, and the gain bandwidth product if you want to evaluate, gain is GM R naught multiplied by bandwidth 1 by R naught C total, so which is simply GM by C total, right. So what is this? This is what is gain bandwidth, in the sense unity gain frequency. This is the frequency for which the gain falls to unity, right, or the gain output becomes equal to input here, right. So this is what is the gain bandwidth product here. So as frequency increases, this becomes unity. Okay, well, okay. So now, so the maximum possible cutoff frequency occurs for an unloaded amplifier, because C total keeps on increasing when you try to add more and more load, right. So C total is equal to obviously how can I write here? There where the capacitive load is entirely due to the device capacitance itself. So therefore C total is a function of the device capacitance is proportional to W. So therefore I will write GBW maximum is equal to GM by C total. I said in the place of C total I am writing it as the function of W, some zeta into W. Okay. Now GBW maximum you can also calculate as K dash VGT by, this is for all the three styles you can calculate. For all the 3 styles you can calculate. Please make a note of this slide. You have to change the equation numbers, all these things you have to remove it. So this all is the all the 3 different styles. This is what is the GBW. Okay. Here you can tabulate all this. You can tabulate all whatever for all the 3 styles, right. What are the 3 styles? Voltage base. Voltage base, the free design variables are WL and VGT, and for the current batch WLID, and for the other batch it's L, VGT and ID. You can calculate GM, G naught, A naught, GBW and GBW maximum, whatever it is. Right. So now what is that? Why we have plotted all the, why you have actually tabulated all this is the question here. So one important observation we try to draw here. So if you want to evaluate the gain multiplied by GBW maximum, right, then you can find that it is ultimately gain into GBW maximum is some 2k dash by alpha, all this, right. Don't read too much into all the what is a lambda, all this is just a function of technology parameters. So the observation is that nowhere your there's no, it's not a function of the voltage, it's not the function of the current, it is not the function of W or L, whatever. That means that when you try to evaluate the gain and GBW maximum product, this is fixed for this topology. If I want to improve it, I can't do it. Nothing is there in my hand. Voltage is not there, current is not there, W is not there, L is not there, right. Therefore what it implies is, if I try to increase, if I want to improve this performance of this topology, I can't. I am pushed to wall. I am pushed to wall. Therefore the only way which is left with me is change the technology, right, or otherwise go for another topology another topology. For this topology common source, I can't do anything more. Not only that, in the common source amplifier, you can just now also see in the common source amplifier, you can also see that between the gate and the drain there is CGD is there, right? This capacitance CGD, right? Now where you are taking output here, I am trying to take output here, and this is the input. But the output and the input, there is an impedance which is in terms of capacitance here. Try to recall the Miller theorem. In an amplifier when there is an impedance between the output and input here, that can be replaced by how? At the input, I'll remove this feedback. At the input, it can be seen as it can be seen as the impedance is Z here. Then it is seen as Z by 1 minus AV. Z by 1 minus AV. So when Z is here, what? 1 by CS, 1 by CGD. So 1 by CGD. So 1 by CGD. So this is the Z which is connected between the output and the input here. So that can be written as Z by 1 minus AV. So Z is equal to 1 by CS or CGDS, okay, into 1 minus AV. 1 is small as compared to voltage gain, so it is AV, right? It appears that the CGD is multiplied by gain times and is appearing at the input, right? So that is actually, that may cause the frequency response to be hampered. So what that means is, if I try to this is the voltage gain and this is the frequency, right? If I try to increase the gain, right? So what is happening? This capacitance which is it's encountering seems to be large, right? So therefore the corresponding pole moves towards the origin, right? So I can say that this unity gain frequency is coming closer to the origin. So available this gain bandwidth is decreasing, right? So larger the gain, the smaller the bandwidth it is, right? So therefore for this given technology I can't improve anymore. Now I want to see that for the same unity gain bandwidth, that is earlier it is like this, right? So this is here, I want to go here, then it is. But if I want to increase the gain, but I don't want to change this unity gain frequency. I don't want to change this unity gain frequency. For the same unity gain frequency, I want to get a larger gain. Then what should I do? That is, I want to get a larger gain here. So for the same unity gain frequency, I want to have this. Okay, I want to get a larger gain for the same unity gain frequency. I can't do anything here, but I should think of a solution. So whenever there is a problem, then if you want to look at the solution, then immediately what we have to look at is who is the culprit, who is causing the problem, right? Who is the culprit and who is causing the problem? Who is the culprit? The culprit is this fellow. This capacitance is between the output and the input. The capacitance CGD is there, right? So that fellow due to Miller, it is getting multiplied by gain terms actually. The larger the gain, the larger you are increasing W, and therefore the larger the C, and therefore actually C is getting even multiplied by gain terms. So therefore what is to be done is since between output and the input the capacitance is there, so somehow you have to resolve it. So probably if you don't take the output from here, take somewhere else here and isolate, that is isolate the output node and the input node. Isolate the output node and the input node. Isolation in the sense who will come to our rescue in the MOSFET technology or the circuits here. No one else come to our rescue, only another MOSFET only will come to our rescue, right? So therefore what I will do, I will use another MOSFET and I will try to isolate what? I will try to isolate output and the input node, right? Because output and input node, if I am taking output here, then the CGD is between the output and input, it is there. I will not take output here. I will try to put another MOSFET here and try to take output from here. Right? Then I am successful in isolating the input and the output node. Right? So this is what exactly I can see that I have isolated the output node from the input node by connecting another MOSFET. This is the cascode topology. So I am trying to get rid of the Miller effect, and therefore I want to improve the performance. Okay. So here you can analyze once again. Okay. So remember, these two transistors are in series, therefore current through both of them are same. Right. We will analyze it with a small assumption. Let us assume that there is a fictitious transistor, because here what is happening, please remember, here signal is applied here only. Here I am giving only DC. Okay. Therefore I can view this as a single transistor, a fictitious transistor, ಊಹಾಜನಿತ transistor, which is taking input from the gate of this is called driving transistor, because this fellow is being driven by the input signal. This fellow is not driven by input signal, but there is what is this voltage? DC voltage. This is a DC voltage to keep this in saturation. Okay. Okay. So therefore this is a DC voltage, all right. Now what we would like to see here is when you try to treat this as a single fictitious transistor, and input voltage is from at the driving transistor, and output is being taken here. Okay. So this is single transistor. Now dou ID by dou VG1 is going to give me the transconductance of that single transistor. GM effective we call. This is for the, not for the this transistor, this is for the circuit. The circuit is viewed as if a single transistor, input here, output there. Dou ID by dou VG1 is the effective transconductance, GM effective. Similarly, dou ID by dou VD2 is the effective conductance, G0. Okay. Well, so again same story. So DID is any current is a function of what? Transconductance is a function of the gate voltage and the drain voltage. I am viewing these two as a compound transistor where input is being taken from VG1, therefore it is GM equivalent into dVG1 plus G0 equivalent into dVD2. Right? Now GM equivalent is equal to dou ID by dou VG1, but by dVD2 is equal to 0, because I want to see the variation in the current only due to the variation in the VG1. So VD2 I am trying to mute it. Right. Similarly, G0 equivalent if you want to calculate dou ID by dou VD2 when dVG1 is 0. Right. So therefore I can now write dVDS2 is equal to dVD2 minus dVS2. VD2, I know that the source of this fellow, see this source of this transistor is the same as the drain of this transistor. So VS2 is equal to VD1, VS2 is equal to VD1. Am I right or not? Huh? Am I right or not? VS2, this is transistor M2. VS2 is the same as VD1. Not convinced. This is the source. S2 and D1 are connected together. S2 and D1 are connected together. So obviously VS2 is equal same as VD1. VS2 is same as so VS2 is same as VD1, and same as again what is why actually what is this 0 here, because dVD2 minus dVS2, right? dVD2 we have made it as 0. Why dVD2 is made as 0? Because we want to calculate GM effective. regarding GM effective, what are we doing? dVdt is 0, only variation due to the voltage at the gate, the current is only due to the applied voltage at the gate of the M1. So therefore this is 0. Now dVgs2 is equal to dVg2 minus dVs2, but dVg2 is also 0. Why dVg2 is 0? Why dVg2 is 0? dVg2 is 0 because you are right, you are there. What is your name? What is your name? Rishi? Trisha. Okay. Good. Even if it is winter, you are working. Actually, you are supposed to work only during rainy season. So, this is. You are right. Tell me. You are right. It is the DC voltage. It's not difference. It is a DC voltage. The DC voltage, therefore, signal I am not applying there. Therefore, delta change whatever 0. There won't be any change there. Am I right or not? So this is dVg2 is or small vg2. It is 0. Right? All the time it is 0. All the time it is 0. Right? So therefore, this is 0 minus dVs2. dVs2 is again dVd1, right? So let's say to move ahead, we'll try to make use of this and substitute here. And so ID, now what I will do is, I'll go back, I'll try to write the current equation for both the transistors separately. Transistor M1 I'll try to consider. Any transistor, for any transistor, current is a function of what? Gate voltage and drain voltage. So therefore, ID is equal to GM1 VG1 plus G01 VD1 for any M1. For M2 it is GM2 VG2 plus G02 VD2. So GM2 VGS2. What is VGS2? VG2 minus VS2. VG2 is 0, 0 minus VS2, VS2 is VD1, so therefore minus VD1. Therefore it is minus GM2 VD1 minus G02, actually this is a plus G02 VD2. When the G02 VDS2, what is VDS2? dVd2 minus dVs2, but dVd2 is 0 because we are calculating GM effective. We have made it as 0. So it says dVd2 is 0, so it is only minus dVs2, but dVs2 is again dVd1. Therefore it is minus dVd1. Therefore this is okay. Now equate both of them and then we'll get VD1 is equal to minus ID by GM2 plus G02. Right. You got that, and then one thing you have to just know, keep in mind, right? So what is that? The gate to source voltage of the transistor is going to change here as the drain voltage of the lower transistor goes up. The value of the gate to source voltage of the upper transistor is going to reduce, reducing its current, right? So if you want, try to look at this circuit, then only you will understand. So what is happening here? What is happening here? Actually both the transistors are in series. Both the transistors are in series. Here only I am applying signal. So in response to the application of the signal or variation signal, the current has to vary, and the same variation should reflect through transistor M2, right? In proportion to what? In proportion to change in the input signal voltage, right? Is it okay? But the question here is, what is happening when this current is changing and all, due to one or other reason, if this voltage changes, VD1 changes, right? If this voltage changes, then what happens? For example, this voltage goes up. This voltage goes up. When this voltage goes up, what happens to this VGS? What happens to VGS? VG is fixed. This voltage is increasing. what happens this VGS2? Decreases. VGS2 decreases, the current has to decrease. The current has to decrease. But we are thinking that the current is only a function of this V in. This fellow is changing, then the current has to change. But due to, suppose this voltage is changing, something dropped here and rest of the things are being dropped here, therefore this voltage also changes. When that is happening, then, and the change is in such a way that this voltage is increasing, then what is happening? This fellow is decreasing, VGS2 is decreasing. As VGS2 decreases, the current is decreasing. So हमारी बात मान नहीं रहा है in total. To some extent, applied gate voltage accordingly current is changing, but what happened is this current change now is not just the function of this V in, rather you can find that there is some slight reduction in the current by the virtue of the variation of this voltage. This is a sort of feedback that you can think of, right? So what is the hint that you will get here is, earlier we thought the current is only a function of variation of this, therefore for this entire circuit what will be the GM effective if you have to see, GM effective is approximately equal to GM1 only, because this fellow same current is forcing to flow through this, therefore total GM for this circuit should be same as of this transistor. But what is happening now? It is becoming slightly less here, because this fellow is causing to vary this voltage, and therefore this GM is decreasing, right? Not only that, also you can see this transistor, the bulk of this transistor is at ground, source is not at ground, therefore there exists a body bias effect. Because of the body bias effect, now as the source voltage of this transistor is going to change, or drain voltage of this transistor, suppose it increases, then what happens? VBS becomes more negative. When VBS becomes more negative, then threshold voltage of this becomes more. When threshold becomes more, current becomes less. So again same story. So the current is not dancing to the tune of the input signal voltage, but some portion of the current variation is also internally, it is a different, right? Which implies that the transconductance GM of this entire circuit is not exactly same as GM1. It is slightly less than the GM1. Mathematically also we can see that, right? I have given the reasons, and then now we will try to see mathematically. So now you try to calculate it. How do you calculate it? So ID is equal to GM1. Now we have seen those two equations, right? From these two transistors here, right? VD1 is equal to minus ID by GM2 plus G02, right? So this we will try to take and try to substitute here in this, okay? So I will try to do that. So ID is equal to GM1 VG1 minus ID into, I will try to substitute this. Is it okay or not? See what I have done from here. I have calculated VD1 is equal to ID by minus ID by GM2 plus G02 from this, right? Okay. So this I will try to go and substitute in the place of the VD1. In the place of VD1, I will try to substitute here. Is it okay? So when I try to substitute there, then this becomes, it is this, and just simplify, and then you will get this is a GM equivalent is what? ID by VG1, ID by VG1, right, is equal to, I will get this expression. So what did you get here? GM1 into GM2 plus G02 by G01 plus G02 into GM2, which implies that GM equivalent is slightly less than GM1, because denominator is greater than numerator. What are the reasons? Conceptually we have already seen. GM effective is less than GM1. Okay. Now if you ignore, because GM is generally greater than G01 G02, if you ignore this, right, and if you ignore this fellow also, then simply it is approximately equal to GM1. approximately GM1, exactly less than GM1. Okay, right. So now we have calculated equivalent transconductance. We want to calculate equivalent G naught. Right. How do you calculate equivalent G naught? So G naught equivalent is equal to dou ID by dou VD2. Right. So with dVg1 is equal to 0. Right. So what is dVgs2? dVgs2 is dVg2 minus dVs2. dVg2 is 0. dVg2 is all the time 0. And so minus dVs2. But what is Vs2? Vs2 is same as Vd1. Right. So it is minus dVd1. Right. And what is dVds2? dVds2 is equal to dVd2 minus dVs2. Right. So dVd2 minus dVs2. Vs2 is Vd1. Right. So dVd2 minus dVs1. Okay. Now, so is it okay? Huh? Any doubt? Should I repeat? So what we are trying to do is G naught equivalent is equal to dou ID by dou VD2. Dou ID by as a single unit. Dou ID by dou VD2. Dou ID by dou VD2 at this node. See impedance in looking into it. Dou ID by dou VD2 with this flow is 0. If this is also there, I can't exactly tell that this current variation is only due to the variation of this voltage. So I'll mute this when the current is a function of two voltages and I want to evaluate the variation of the current only due to one voltage. I have to mute. So this flow is muted. So therefore this becomes dou ID by dou VD2. Dou ID by dou VD2 with dVg1 is equal to 0. This Vg1, right? This flow is 0. Now I am just writing expressions. dVgs2 is equal to, what is dVgs2? dVgs2 is dVg2 minus dVs2. Vs2, right? dVg2 is 0. So it is minus dVd1. Why? Because Vs2 is same as Vd1. And what is dVds2? dVds2. dVds2 is dVd2 minus dVs2. dVd2 minus dVs2. So dVs2 is same as dVd1. So it is dVd2 minus dVd1. We should not get confused. Earlier we made dVd2 is 0. Now also no. Earlier for the calculation of GM effective, we made dVd2 is equal to 0. We made dVd2 0 for the calculation of GM effective. Here what is that you are assuming? dVg1 is 0. Right. So this one. Now ID is equal to for both the transistors I would like to write. Okay. So what is the current now ID? It is transistor M1. I will write it as GM1 Vg1 plus G01 Vd1. Right. GM1 Vg, I am writing for this transistor separately. This transistor separately. GM1 Vg1 plus GM2 Vd2. Right? No. For transistor M1 I am going to write. Then write transistor M1, it is GM1 Vg1 plus G01 Vd1. G01, but transistor M1 only I am writing. So GM1 Vg1 plus G01 Vd1. But GM1 Vg1 is 0 because I am calculating this fellow. Na? So Vg1 is 0. So dVg1 or small Vg1 are the same. Therefore this fellow is 0. ID is equal to G01 Vd1. Right. So and from here what is Vd1? Vd1 is equal to minus ID by minus ID. ID by G01. Very good. ID by G01. So all of you are not sleeping. Now ID is equal to now what I will do, I am trying to take the transistor M2. Transistor M2, what is ID? ID is equal to GM2 VG2 plus G02 VD2. Excellent. So GM2 VDS2 I should write. GM2 VDS2. Earlier we are not pronouncing S because it is already ground. But this is not at ground, so I have to write GM2 VDS2 plus G02 VDS2. So GM2 ठीक है, VDS2 is already we have written. So VDS2 is VD2 minus VS2, but VD2, so this is dVD2 minus, in the place of VS2 it is VD1. VS2 is VD1. So therefore this fellow here I am trying to write here. So minus GM2. So what is this expression here? This is now GM2 into this is VGS2, right? VGS2 is VG2 minus VS2. VG2 minus VS2. VG2 is all the time 0. That's what I am telling. VG2 is all the time 0. I am expanding, that's all. For this transistor, all the time VG2 is all the time it is DC only. For the upper I am not giving any signal. Signal is being given over to the bottom transistor. Now that also I am not giving. Don't think that earlier I have given to bottom transistor, now I am given to upper transistor. नहीं कर रहे हैं भाई. Not that. See, upper, yeah, you see upper transistor in this sense. In the signal, this is the signal is earlier we have given here. Now we are muting this, but here this voltage now we are considering. This voltage variation we are considering, but this voltage all the time is DC. Where output impedance means what? Dou VD2 by dou ID. So variation is at the drain node of the upper transistor. dVD2 by dou ID, dID. Understand? Not this gate voltage. Gate voltage is all the time DC I am giving to keep that in saturation. So therefore this is a GM2 VGS2 when you try to calculate. GM2 into VZ2 minus VS2. VZ2 is how much? 0. VS2 is VD1. So therefore it is minus GM2 into plus G02 into VDS2. VDS2 is VD2 minus VS2. VS2 is VD1. Is it okay? Right. So any doubt? Now just it's a matter of solving this, that's all, right? So from here I am trying to write ID is equal to what I am trying to do. I am going to substitute here. What I am going to substitute here? So from here, so ID is equal to substitute whatever is the VD1 there. So just to solve this, I will get straight away G0 equivalent is equal to ID by VD2. If you solve, I will get this as the. So here once again GM is larger than these two, therefore you can ignore this. Then this becomes G01 into G02 by GM2. Or R0 equivalent is equal to ulta karo GM2 by G01 G02 or GM2 R02 into R01. GM2 R0 equivalent is equal to GM2 R02 into R01. What does it mean? It means that when a single transistor was used, the output impedance was R0 or R01. Now it is impedance seen will be GM2 R02 times R01, right? So the output impedance is enhanced by a gain factor GM2 R02 times R01. It's a big boost in the output impedance. It's a big change in the output impedance. Is it okay? So output impedance is increased by a gain factor. Okay. So now you can calculate what is the gain. You want to calculate the gain here. So gain is equal to minus GM equivalent divided by G naught equivalent. So the gain is minus GM equivalent by G naught equivalent. So already you calculated GM equivalent and G naught equivalent, just substitute there. You will get this is the expression for the gain. Okay. Again, what is the observation here? Observation is this gain is corresponding to the common source amplifier. Yeah, I just have to mention you that this cascode is a combination of, this is a common source. Source is common between the input and the output. And this is fellow, this is a gate is a small signal ground because DC is not, only DC is there. So therefore, where it is taking input? Taking input at the source, and it is delivering output at the drain. What is common between the output and the input? Gate. So it is a common gate. So a combination of common source is the cascode. So the gain for this fellow is GMR naught. Okay. So that is GM1 by G01 or GM1 R01, and for the common gate amplifier this is the gain. So overall gain is A01 into A02. Okay. So this is what the DC gain, this is what the DC gain, and you can also see that this gain actually, if you ignore this fact, if you ignore this one, then if you try to multiply GM, if you assume that GM1 is equal to GM2, G01 is equal to G02, then both are equal to GM1 is equal to GM2 is equal to GM, G01 is equal to G02 is equal to G0, then the gain will be GMR naught whole square. If you ignore this, it becomes GMR naught whole square. So see that in the cascode, the gain is improved by leaps and bounds. GMR naught square, so a huge improvement in the gain. Right? This is DC gain. Huge improvement because we have not considered the capacitances, not included capacitance. Right? Now I will try to consider the capacitance also. So when I try to consider the capacitances, these are the capacitances, CG1, CGD1, all these things, right? But how did I draw this small signal equivalent circuit is the question. So for the first transistor, it is no issue here. This is the gate, this is the source. So between the and what is this? This is the, see, this is the gate I said, right? Gate, and this is the drain, right? Between the gate and drain, CGD is there, and drain and the source is ground. So there is a voltage dependent current source, GMVGS, whatever it is, and R01 parallel. Till this no problem at all. But then here comes the second transistor. How do you put this small signal equivalent circuit? The question for the second transistor, okay. Eraser. Second transistor, where is the source of the second transistor? Leda కొంచెం పైకి చేయండి. ఇంకొంచెం పైకి బస్. Okay, thank you. Where is the source of the second transistor? So this is a S2 and this is a D1, right? So if you try to plot, this is what is my G1 and this is my D1. This is voltage dependent current source, and there is a capacitance here, right? And there is a capacitance here, and this is the resistance R01. Now for the transistor M2, this gate G2 is a small signal ground. gate G2 is at a small signal ground. So gate is at small signal ground and D1 and S2 are connected. So D1 and this should be S2. D1 and S2 are connected. Don't move away from the frame. D1 and so your identity card is valid till tomorrow. Okay. So D1 and S2 are connected. Okay. And where is my D2? So this is a D2 here. So between the D2 and S2, I have to write what? The voltage dependent current source. For a MOSFET, the way I have written here, between D1 and S1, the voltage dependent current source. The current will flow in response to the operating gate voltage, right? So therefore, the current is flowing from drain to source, right? This is from drain to source, right? So I should represent it by drain to source, right? This is GM2 VGS2, GM2 VGS2, and parallel to this there will be a resistance R02. In parallel to this there will be resistance R02. Okay, and so at the here this output node, right, whatever the capacitance is there at this node, all these equivalent capacitors put together, I will represent it by C0. Okay, but here so this is a if you represent this node as X here, if you represent this node as X, okay, so this is GM2 VG2 S is now X, so it is VG2 EX. Am I right or not? But what is VG2S? Actually VG2 minus VS2, right? So that VG2 is 0, right? So it is just like it's VG2 minus VS2. S2 is X here. This is 0, so it's a minus VS2 or minus Vx. Am I right or not? So if you permit me, I will write this VGS2 as minus Vx. Am I right or not? So this is minus GM2 Vx, minus GM2 Vx. Minus अच्छा नहीं लगता. Great. What is your name? Snigdha. Okay. So okay. So this is my GM2 Vx and R02, right? R01, and that's all. This is what is small signal equivalent circuit for the cascode. Now what I have to do? Same again, KCL I have to do, and then I have to evaluate. Ultimately I have to evaluate the transfer function. What is the transfer function? V0 by V in I have to calculate. So little bit of math you have to do here. I am now ignoring this math because it takes time. So we'll focus more on the concept. So if you evaluate all that, probably you will get it as this is the Vx here, and then substitute that, and ultimately you will get V0 by Vi is A1 A2 by 1 plus blah blah blah. You will get. Okay, this is the actual total transfer function, and if you assume that SR01 CDG is small as compared to A1, that is for the frequencies at which SR01 CDG is small, right? Omega is frequency and CDG is of the order of the femtofarads obviously. So therefore for those frequencies I can safely ignore. Then I will say that this is simply equal to A1 A2 by blah blah blah, right? Again, when omega is 0, S is equal to j omega, right, and omega is equal to 0, what is a DC gain is simply A1 A2, what we have already derived, right? So This is and also what you can just now think is R01 is approximately equal to R02 and 1 can be ignored as compared to A2. Then this is A1 A2 by 1 plus SR01 C0 A2, right. So if you try to evaluate the this one, the bandwidth, right, if you try to evaluate the bandwidth, what happened to bandwidth here, bandwidth is equal to, bandwidth is omega is equal to 1 by R01 C01 into A2, 1 by R01 into A2. Earlier bandwidth was 1 by R01 C01. Now DC gain is multiplied by A2, whereas bandwidth is reduced by A2. This is 3 dB bandwidth. But when it comes to the unity gain bandwidth, it is GM by CL. GM effective is GM1 only, so GM1 by CL only. Therefore, unity gain bandwidth remains the same. Unity gain bandwidth remains the same. I have drawn here somewhere. Unity gain bandwidth remains the same as the single transistor amplifier, but the gain is increased by A2 times. But 3 dB bandwidth comes down. That I agree, right? So unity gain, for the same unity gain bandwidth, I am able to increase the gain by A2 times. Right? So this is what is the advantage of the cascode. Okay. So if you want to design the cascode amplifier, how do you go ahead? Initially, some specifications are gain is equal to, it will be given to you, and then gain bandwidth product is 100 megahertz. Our professor is there, Jairam, just to tell him that this also he has to do it for the 180 nanometers. Okay, tell him that. So this is the DC gain is given, and gain bandwidth product will be given to the unity gain frequency will be given to you, and then load capacity assumption some value. Now I have to start doing the design the cascode amplifier. How do I design the cascode amplifier? The question. So what I will do first of all, single transistor amplifier, how do you design? You design that. No, there also gain is given to you. So load capacity is assumed. Therefore, what you have done there is for single transistor amplifier, gain is equal to GM R naught, right? Gain is given to you, and then bandwidth also 1 by 2 pi R naught CL. So therefore, what you will do, CL is given to you, bandwidth is given to you. Therefore, you can calculate what is R naught. Once you calculate, because bandwidth is 1 by 2 pi R naught CL, CL is assumed, bandwidth is given to you, R naught you are calculated, R naught is equal to 1 by lambda ID. Therefore, you know R naught now, R naught 1 by lambda ID, lambda is known to you, ID you will calculate, you got the ID now with you. Gain is given as a specification, gain is equal to GM R naught, already R naught you have calculated. So gain is given to you, calculate GM. GM is equal to square root of 2 ID mu C of W by L. So already ID you have calculated in the gain expression, in the GM expression, right? So simply you substitute, already GM you know, ID you know, and therefore you W by L you have to calculate, right? So it is not VGS, it is a W by L, right? That's all, design is over. So similarly for the cascode, how do you do that? For the cascode, how do you do that? For the cascode now, these are the specifications, right? So you start moving now, stating that don't just follow this, I just now make slight changes here. So gain bandwidth the product is given to you. Gain bandwidth product is as a given as specification, it is GM by C, GM by C. So GBW is given to you, it is a GM by C. C is total load capacitance. So you know CL and you know GBW, and try to calculate what is GM, right? So you can calculate what is GM1. Once you calculate GM1, and I know the gain is equal to what? I am assuming that transistor for M1 and M2 both are having the similar GM and R naught, right? Then the gain is simply GM1 R naught 1 into GM2 R naught 2, right? So the total gain is given to you. So 2500 is equal to GM1 R naught 1 into 1 plus GM2 R naught 2, right? Or if I assume that GM1 is equal to GM2 and G01 is equal to G02, then it is simply A into 1 plus A, right? Therefore, you can calculate what is A from here. Once I know what is the A, what is the A here? A corresponds to the intrinsic gain of each of the transistor. Intrinsic gain of each of the GM R naught of each of the transistor. So once you know GM R naught of each of the transistor, you know, and for the lower transistor already you have just now seen that it is GM1 by C, right? What is the GBW? You have already calculated G1 by C. From the GM1 you already calculated. But you know GM1 and you know what is GM1 R0 is equal to this. So from that you can calculate what is R01, right? So you can calculate what is R01. Okay. So once you calculate R01, you need to follow this. You can just simply R01 is 1 by lambda ID, R1 by lambda ID. You know lambda and R0 you know, that from that ID you can calculate. So once you calculate ID here and use that expression here and calculate WL. So the same WL for both the transistors. So cascode design is also over, right? So what you have done for the cascode design? Let's try to recapitulate. What are the specifications given to you? Gain bandwidth product is given to you, which is GM by C, GM1 by C. C is assumed, so gain bandwidth product is there, is GM1 by C, therefore GM1 you calculate. Once you have done that, what is the gain here? Gain is equal to, it's also a specification given to you. So gain is a 2500 whatever is gain given to you, and you know the gain is equal to, I said that it is a 1 into 1 plus A2, right? Assuming that A2 is equal to A1, the GM are not the same for both of them, A into 1 plus A, equate that and try to get what is A. Right. Once you know A is equal to GM1 R01. Already GM1 you have calculated, substitute that. Right. So you will get what is R01. And I know R01 is equal to 1 by lambda ID. I know lambda, therefore I will calculate ID. And once I know ID, I know GM value. GM1 already we have calculated from the gain bandwidth expression. GM is equal to square root 2 ID mu C of WL. Right. Therefore, I know ID, I know GM, and I simply calculate WL1. WL1 is same as WL2. Khel khatam, dukan. Right. So this is the story of cascode. Okay, and let's try to move towards you have patience. Should I close? Huh? So, what is time? 6. It's your choice. Pardon? We can't say, but then whenever you say stop, I'll stop, that's all. Okay? Whenever it's saturated. Okay. So very quickly, let's try to see. I'd like to mention here one thing. This is a simple common source amplifier. The question here is, actually I should have dealt in the beginning itself. If you want to design the amplifier, then which region you are supposed to bias is the question. In which region you want to bias? If you want to design the amplifier, in which region you want to bias the transistor? You know that there are 3 regions. What are they? So obviously, I think you will not prefer cutoff region. Right. So what is left over is cutoff. So sorry, saturation, linear region. So don't say active. I never said anything activity active. So I don't know what is active. Right. So linear region and saturation region. Which region do you prefer if I want to design an amplifier? In the question. Snigdha says linear. Constant, I want to amplify now. So how do I do that? Then linear. Huh? So quickly change. Huh? In which region you want to know the bass? Huh? Saturation. Why? Because you are saturated. Huh? In which region you want to bass? Why? Constant current, but what you want to amplify it. If the current is constant, you can't just do that, no? Right. So okay. So let's not. Already you are exhausted. When you want to, I think that will be answered a few minutes later. Let's first look at this. Now let me try to consider this circuit here. what is happening? The input voltage is varying here. Then now I want to plot the output voltage. Very quickly, what is going to happen as the input voltage is greater than threshold voltage, till there is a threshold voltage, what happens? This fellow, Arey bhai sahab, when the input voltage is less than threshold voltage, transistor is cut off. There is no current. Wherever there is a flat saturation, there is nahi hai. Right. So here, when the input voltage is less than threshold voltage, there is no current. No current is flowing. Vout is equal to VDD minus ID RD. Vout is VDD minus ID RD. ID is 0. Right. So potential is only VDD. So it's a VDD is there. And now what happens? When the input voltage is greater than threshold voltage, then some current flows, therefore there is a drop, ID RD, and therefore Vout is equal to VDD minus ID RD. Then as the input voltage is greater than threshold voltage, the current starts increasing, therefore voltage drop ID RD also increases, therefore Vout starts decreasing, right? So Vout is equal to VDD minus ID RD. Since ID RD is increasing, Vout should decrease, right? So Vout keeps on decreasing. But in this region, transistor will be in which region? I don't know. During this portion, transistor will be in saturation or in the linear region is the question. Immediately after the cutoff, transistor will be in which region? Transistor will be in which region? Immediately after the cutoff, will it go to saturation? Linear region. So, how do you say that? There is saturation or cutoff or linear region, whatever. What is the condition? Pardon? Who said linearly? I didn't say anything. It all depends upon which region it is. Right? So, in which region, how do you judge is basically VDS is greater than VGS minus V threshold, then transistor is saturation. If VDS is less than VGS minus V threshold, this is linear region. So, here VDS is Vout only. In this portion, VDS is almost equal to VDD, it is closer to VDD, right? And VGS minus V threshold, it is just above threshold voltage. Let us say threshold voltage is 1 volt, applied voltage is 1.1 volt. VGS minus V threshold is input voltage is 1.1 volt, threshold voltage is 1 volt. What is VGS minus V threshold? Input voltage is 1.1 volt. That is VGS is 1.1 volt. Threshold voltage is 1 volt. So what is VGS minus V threshold? 0.1. So it is such a small value. VGS minus V threshold is such a small value, whereas VDS is closer to VDD. So which is larger? VDS is larger or VGS minus V threshold is larger? VDS is larger or VGS minus V threshold is larger? VDS is larger. When VDS is larger than VGS minus V threshold, transistor will be in which region? Saturation region. Therefore, the transistor here will be in the saturation region. Right? So, as you keep on increasing the input voltage, the current keeps on increasing, therefore drop keeps on increasing and output voltage keeps on decreasing. So, VDS keeps on decreasing, therefore, that means I am always comparing VDS with respect to VGS minus V threshold. Now, VDS is decreasing and VGS minus V threshold, because VGS is increasing, this flow is increasing, right? So, this flow is decreasing, this flow is increasing. For a specific value, this will become equal, and further this may go higher. VGS minus V threshold will go higher as compared to VDS. Then the transistor will enter into linear region from saturation. So, therefore, for a specific value of the input here, the transistor enters into the linear region. So, that's all. Now, why should I worry about all this is because whenever I want to evaluate any GM or blah blah blah, in which region it is I should know, then only I will apply the corresponding expression for the current, right. So, this is what is possible equivalent circuit here, and I can calculate the gain is equal to minus GM V1 into RD is the output voltage. So, divided by input voltage is a V in. So, this simply gain is minus GM1 RD. Okay. So, now you can in the different regions you can calculate what is the gain here. Okay. I don't want so as I said, now when it enters into the deep triode region, when it enters into the, because you keep on increasing the Vn, then it enters into deep triode region, then I can replace the transistor by resistance also, right? So I can it just appears like this. So it appears like how it appears. Just see here, it appears like a transistor in the deep triode region. This is like a resistor. This is like a resistor here. It is just a voltage divider. Okay, just a voltage divider. Okay. So now, in the place of the resistor, the gain of course is all the time we calculate Gm minus Gm already. Okay. Now let me try to just now see. Therefore, if in the resistor in this mode I can it is a voltage divider I said. Then VDD by R on plus RD into R on. So substitute what is R on here. This is no big deal. And this is for the saturation region. Now what I would like to do is in the place of resistor load, I will try to replace the current source the way we have done earlier and try to calculate the gain, which we have already done it. Okay. Now there is an interesting experiment which we would like to do it. What we would like to do here is, by varying the input voltage, we would like to plot Gm. By varying the input voltage, we would like to plot Gm. So the same circuit which I have done, resistive load. When you keep on doing that, when the input voltage is greater than threshold, less than threshold voltage, current is 0, Gm is 0. When the input voltage is greater than threshold voltage, what will happen? Transistor is entering into which region? Immediately, we said it is a saturation region. Further circuit, there is no hard and fast rule. That circuit is a. So then I have to take the expression of the Gm for the transistor which is in the saturation. What is the expression for the Gm which is in the saturation? Gm is equal to, you have already calculated, right? ID is equal to half mu C ox W into VGS minus whole square, and dou ID by dou VGS is equal to mu C, what is that? 2 gets cancelled, the mu C ox W into VGS minus V threshold. Mu C ox W into VGS minus V threshold. So that means it is simply linearly varying with the VGS, right? Or Vin. So as Vin is increasing, the Gm is varying linearly, increasing with respect to input voltage as it increases. But when it reaches this point here, there the transistor is entering linear region, therefore I have to use the corresponding expression for the linear region. Then again Gm I have to calculate for the linear region. In the linear region I have to write the current equation again. ID is equal to mu C ox W into VGS minus V threshold into VDS minus VDS square by 2, and then try to dou ID by dou VGS to calculate, then it becomes mu C ox W into VGS minus V threshold into VDS. You will get it and do it, right? So that means it is now proportional to VDS. Gm is proportional to VDS. So but what is happened to VDS here? As input voltage is increasing, VDS is decreasing now. Therefore, Gm keeps on falling. Gm keeps on falling, right? So now the question that I posed earlier, that is, in which region should I bias the transistor if I want to use it as an amplifier? That's the question, right? Right. So if you use in the saturation, what is going to happen? The Gm is increasing, but in the linear region, it is falling. It's falling. No one wants that. Sensitivity should be low, right? Gm is sensitivity, and therefore gain is Gm or not. And therefore, you don't want that to happen, and therefore, obviously, the preferred reason is saturation. Not only that, actually, what we would like to do is, if you try to bias it in the linear region, the current is also a function of VDS, because in the linear region, current is also a function of VDS. So, but you would like to have the variation in the current to respond to only applied signal variation at the gate, that is at the input, but you don't want the current to vary due to some voltage variation at the output. Due to some other reason, load varies, that also varies. I don't want that, right? So when just like you are in the class, and the teacher always wants that when he speaks, then all the class should listen, and then, right? But if he speaks and the others also speaking, then ultimately chaos. You don't want that, right? Therefore, you want that this current should vary only in response to signal variation, but not to that load varies due to some other something else is also varying. You will never know the variation of the current is due to the variation of signal or something else, and therefore, but always we feel that, oh, output is varying, oh, because the input is varying, output is varying. But if it is in the linear region, even if the output voltage varies due to some other, that also varies. That is a wrong interpretation. Therefore, we feel that the current should only dance to the tune of signal that is applied at the gate, right? Understand? Therefore, the transistor should be in which region? Saturation. Those are the two regions which you can just attribute, right? All right, so you can always calculate, right? So how do you maximize the gain is the question here. So she has already given a signal to signal, the signal that is already saturation, very good. I am happy that we learned a lot of things. Let's try to tell that now, close it. Is that you are telling? So gain is equal to, how do you evaluate the gain here? So the gain already I have just GM already. So what I have the minus GM already, GM is minus square root of 2 mu Cx W by L into ID, actually ID is there inside. The ID, so this is actually gain. What is gain is minus GM RD, right? What is GM? GM is equal to square root of 2 ID mu Cx W by L, right? And RD I am writing some trickish fashion. RD I am writing it as VRD is ID RD. VRD is ID into RD, right? So what is RD? How do I write RD as ID RD by ID? ID RD by ID. I can write ID RD is VRD. So VRD by ID. But under एक ID था, therefore it gets cancelled and then it becomes square root of ID here. So this is the gain expression. Now look at this expression. I want to maximize the gain. How do I maximize the gain is the question. How do I maximize the gain is the question. How do I maximize the gain? So by increasing W by L, decreasing current, or increasing this, all things are possible, right? But that's an electa. If you want to just go for increasing W by L, what happens is the capacitance, parasitic capacitance also increases, therefore speed is at stake. If you want to increase VRD, then power dissipation is at stake, right? So because IDRD increases, then dissipation, power dissipation increases, right? So therefore there are so many trade-offs are there. If you want to maximize the gain, there are so many trade-offs are there between the gain, bandwidth and the speed, whatever it is, right? So that you have to keep in mind, and I don't want to. So what you understood now is that if you want to design an amplifier, there are so many things you have to, a lot of trade-offs are there. So कुछ तो therefore जब आप कुछ you want to पकाना चाहते हैं, you want just to prepare something, then you want to make it balanced. Is very difficult, right? You want to have some taste, right? You want to have some sour taste, then probably something else will do, right? So add salt or this or that. Then BP patients are there, then you don't want to add BP, and then what happens? So therefore these all are the trade-offs. So there is a now coming to this one. This is called here gate and drain are connected together. We call it the diode connect transistor. Is there a diode connect transistor? Here very quickly we'll try to, without going to math, we'll try to say that this transistor, whether it is in saturation or not, is a question here. Why you want to look that is, I'll tell later on. So because gate and drain are connected together, in which region it can be in the sense all the time here what is VDS? VDS is equal to VGS here. Am I right or not? VDS. This is the drain. Drain. This is drain. This is the source. So VDS is same as VGS because drain and gate are connected together. So what is the condition required for the transistor to be in saturation? VDS should be greater than VGS minus threshold. So since VDS is equal to VGS, then I can always say that transistor is always in the saturation. When this fellow is in saturation, therefore can I use it as a current source is a question. Can I use it as a current source or not is a question. Who? Oh, this fellow is call him. Video time is over. I want to go. So not you. आपके पीछे वाला. He is there outside. He went there with his mobile.
Sir, good evening, sir. I can.
వీడియో వాళ్ళ ఫోన్ చేశాడా? వీడియో అని ఫోన్ చేశాడంట. అంటే అవర్స్ అయిపోయినాయని లేదా? ఓకే సరే ఇంకా బాగుతూనే ఉన్నాను. ఓకే రైట్. Since they asked, I'm going to continue that, sir. So I'll stop it whenever Sigda says. Okay, right, sir. Stop in 10 minutes. Right. These people will beat you. So stick is also here only. Right. So this is. I'll try to just give some conclusions now. I'll not go into math and all. Try to give conclusions very quickly. So this is the gate and drain are connected together, and therefore this is now we have seen that this transistor is acting in saturation. All right. This is acting in saturation, but then can I use it as a current source or not is the question. If I want to use it as a current source, what is the requirement? Again, voltage. even if the voltage, this voltage varies, the current should not vary. Even this voltage varies, current should not vary. So, but in saturation, no, therefore it appears that I can use it as current source, right? Is it true? Appears to be, but all things which are appearing may not be true. So we can see that as VDS is varying here, VGS is also varying, because drain and gate are connected together. Drain and gate are connected together. As VDS varies, VGS also varies. As VGS varies, current is bound to vary. As VGS varies, current is bound to vary. Though it is in saturation, but because VGS is also varying, obviously, see earlier what we said is as VDS is varying, keeping VGS constant, current is constant. But here, I am violating that rule. That the mutual funds risk factor, we have not studied it properly. Therefore, what happened? Here VDS is varying, but VGS is also varying. Therefore, current is varying. Therefore, it cannot be used as a current source, right? But anyhow, I can use it as a load, simple load, and I can design some simple amplifier, right? So this all is the math here behind, and then I'll try to evaluate what is the impedance looking into that with simple by drawing the small signal equivalent circuit, and I'll try to evaluate the, and then the impedance looking into this by applying some voltage, and try to evaluate the current Vx by X. That gives me the impedance, that is 1 by Gm. That is 1 by Gm is the impedance. Gm is generally large, therefore 1 by Gm is small. Therefore, if I use this as a load, then if I use this as a load, then obviously, since the impedance looked into this is 1 by Gm, then gain is Gm R naught minus Gm into right. Therefore, since impedance is small, then obviously gain will be small. This is through intuition we can tell without doing any math and all. Still, if you want to go with it, you can go with it. But it's a simple elegant circuit here. So the gain is simply minus Gm into R naught. R naught is 1 by Gm, I said. So there is a body bias effect here. By taking the body bias effect, is actually equivalent Gm is this. So gain is simply minus Gm into R naught. But I can, how do I get this is a question here. Simply I know that this is minus Gm1 by Gm2 approximately. So Gm1 is square root of 2 ID mu Cx W by L1, and this is square root of 2 ID2 mu Cx W by L2. But ID1 and ID2 are same because both of them are in series. So everything will get cancelled. Only it's a function of the ratios of the geometries of the two transistors. Therefore, the gain is just simply ratio of the geometries of the two transistors. So simple. So vary the WLs, happily you can get to the variation in the gain, but then the happiness doesn't last for long because the gain is limited, right? So this is what is such a simple circuit here. But then if you don't want body bias effect, then obviously I said in the beginning itself, keep that PMOS transistor here direct connected, then there won't be any body bias effect. Therefore, but then a factor of mu n by mu p will come into picture. Well, so this is what is your a simple what called a common source amplifier with diode connected load, and there is here the constraints here that you can just think of is that constraints are that the gain is very much limited, number one. Number two is the difference between the two transistors, the geometries of the two transistors will be too large here, even for smaller gains that mathematically you can see. And also is the overdrive voltages is a problem here, right? So there is the overdrive, you need to have a larger overdrive voltages, right? So these are the problems which are associated with this one. Now, if you want to get rid of that, what is the solution here? The solution is only simple: diode connected transistor by ek namaskar. Then remove the diode connected transistor, and then what you will do? Just try to put a ordinary current source, because that is not behaving like current source. I want to have a larger R naught there, so I will try to put a current source. So current source in this is what? Because the gate and the drain you have connected earlier together, so now you are removing that connection, because why did you connect earlier? Telugu we call Ullu Badakam. So therefore we don't want to derive this voltage from somewhere else. So therefore we want to just easily connect this one here. Therefore this voltage will be derived from here, right? But you know that the very shortcut has got its own disadvantage. Therefore now you try to derive. There is no alternate. There is no shortcut here. You derive it from somewhere, and therefore you try to have a beautiful current source. Now all right, it's okay, right? You are able to right. Then this is what is the gain and all, right? So this is the gain is you can calculate the gain and all using that. So okay. Now quickly we would like to just know one more variation here is for the common source amplifier. We when you try to give a voltage at the gate, and then you have seen that the current is a function of what? ID is equal to half mu C of W into VGS minus the whole square. For small variation in the VGS, then there is a square law relationship is there. Therefore, the current variation is varying leaps and bounds. Sometimes we don't want that. Sometimes we don't. We want to have a linear relationship between the applied voltage and the resulting current. So therefore, we want to reduce the sensitivity. So what I will do is, I will try to connect a resistor in the source here. Then what happens? So when I give an input voltage V in here, a portion of the input voltage is getting dropped here. The only therefore effectively available VGS is, but the same V in, is applied. I am not changing the V in. V in remains the same, but the portion of that only appears between the gate and source. A rest gets dropped across RS, and therefore what is happening is, the effectively available gate to source voltage is going to be reduced, and therefore the current variation becomes less as for the V in variation. So this is called a degenerative source degenerated common source amplifier. So okay, you can just now do the analysis, and the equivalent transconductance is GM by 1 plus GMRS. Okay. So I will not go into the math here, and the corresponding this one is here. Okay. And then it is interesting to evaluate this all is mathematical evaluation. It is a GM by 1 plus GMRS. You can easily say that when RS is very large, right, then what happens? This fellow is very large as compared to this. This goes off. GM is equal to 1 by RS. So equivalent transconductance is simply inversely proportional to the resistance. Therefore linearization took place. Or if RS is very small, then what happens? This is R is very small, let us say 0, then it is simply capital GM is small gm only, right? There is no big deal over there, right? So this all is about the common source amplifier with the source degeneration, okay? And it is interesting to evaluate the output impedance of the common source amplifier with source degeneration, and then you can see that the output impedance is going to be increased, right? Output impedance is going to be increased. It is not by surprise. The reason is, what is happening is dou ID, the variation in the current here, is becoming smaller, right? So because there is a negative feedback, whatever is the voltage that is dropped across the resistance, that is reducing the effective input voltage, and therefore you can see the variation in the current is small. So because variation in the current is small, impedance is more. This is simple intuition you can say. Therefore output impedance is larger. Therefore that is you can always prove it through the mathematics here. Okay. Therefore this all is that math and all. And we will try to quickly move towards, we will not do all this. The cascode we have seen it enough, probably will not deal much about that. Yeah, a cascode, I just would like to mention one thing, that in the load of the cascode should always be another cascode. Otherwise what happens, whatever you have improved the output impedance, that get lost. If you try to, the cascode I have designed already, but you try to put one useless resistance over there, whose resistance value is less than the improved resistance, it comes in parallel with this, and therefore when two resistances are in parallel, then obviously equivalent resistance is smaller than the smaller one. Right? Therefore that's meaningless. Therefore try to put in the load also as a cascode, right? Then what happens is you will get a larger impedance, okay? Therefore larger output impedance, larger gain you will get. The another important property for the cascode is the shielding property. Of course we have said that the shielding property, in the sense what is happening here. So the cascode can be viewed as if there is one transistor, this lower transistor is a RS is replaced by resistance. So it's just like a source degenerated common source amplifier. Why? In the sense, when you are going to evaluate the output impedance, you are going to evaluate the output impedance. How do you evaluate output impedance? When you are going to evaluate the output impedance, you are muting the input at the bottom of the gain transistor. I am not giving in the input signal. When I am not giving in the input signal, it is just like a resistor for me. Therefore there is nothing wrong in just replacing it by a resistor, right? So therefore the bottom transistor, driving transistor is a resistor, right? Now what is it I am doing? I am evaluating the output impedance. When I am going to evaluate output impedance, how is it I am evaluating output impedance for any circuit? I will mute the input signal, I will try to apply a voltage at the output node and give some voltage and try to evaluate dou Vd by dou Id, that is the output impedance, right? So here also when I am trying to do that for the cascode, then you are muting this fellow at the bottom transistor, the driving transistor. When you do that, it is just like a resistor. So therefore then it just mimics like. And how about the upper transistor? Upper transistor anyhow gate is a DC voltage, that why I say though, that is always ground only, right? So just like this is a common source amplifier with a source degeneration, and here now I am trying to apply some voltage change, and then I try to evaluate for delta V what is delta Ix, right. I want to evaluate. When I try to do that, so that can be seen as if this is delta V, right. So this delta VRS is equal to delta VRS. This is the delta V is applied here. This is total delta current. I can view because this potential is same here and here also. I can view as if delta V is here, delta V is here. So delta V here, delta V here. So therefore, I can view this further as if what the impedance in looking into this is 1 by Gm plus GMB. Therefore, I will replace this by a resistor with the resistance of 1 by Gm plus GMB. So this is simply 1 by Gm plus GMB and grounded, and this is R naught, this is delta V, and this is delta VRS, right. Delta VRS is what is the voltage drop across the resistance RS in response to change in this is delta VRS, right. Now, so delta VRS, what is this voltage here? If there is a change here delta V, what is delta VRS we want to evaluate? Delta VRS is equal to delta V multiplied by, where is delta V? Delta V I am giving here, delta V multiplied by, divided by, what is this? This is R naught plus, these two are in parallel, R naught plus RS is in parallel with 1 by Gm plus GMB, right. RS in parallel with 1 by Gm plus GMB. So all this gives me current here multiplied by 1 by Gm plus GMB in parallel with RS. That because I want this voltage, right. Did you understand or not? What I am trying to do, I am giving a delta V here. I want to evaluate what is this voltage delta VRS here. How do I do that? Delta V divided by delta. First of all, I am calculating current here. Delta V divided by R naught plus these two in parallel gives me the total current. That multiplied by these two in parallel gives me voltage here. That is what exactly I have done there, right. Delta V divided by 1 by Gm plus GMB in parallel with RS plus R naught, the current multiplied by 1 by Gm plus GMB in parallel RS. So if you try to do the small evaluation, what I am getting here is, so what here by inspection itself I can say this delta VRS is now in the numerator and denominator. If you try to compare, numerator is larger or denominator is larger? Denominator is larger because denominator has got R naught plus this all is there. R naught is big, so denominator is larger. This itself clearly demonstrates that delta VRS is only a fraction of the delta V. Delta VRS is only a fraction of delta V. So if there is a change in the output node here by delta V, only a fraction of that only appears at this node, right. So it is as good as I am driving a vehicle, right. So the road I am just trying to move from Vijayawada to Challapalli, there is a village there, right. So when you try to move there, then the road here after Pamaru there is another town, then you start all movie will be appearing in front of you. Then there is a lot of variations are there, the ups and downs on the road, and therefore your back will be spoiled. Therefore what you will do, you will prefer to have good shock absorbers for the vehicle. Then it absorbs all the bumps, right. It will not allow to reach to your back, right. Therefore exactly the same thing here. Therefore if there is some variation here that is being dropped here, only a fraction of that only appears to reach in the top here. What is this node? This node, what is this node? This node is the drain of driving transistor. That node is the drain of the driving transistor. So beautifully, it is acting like a shock absorber, right. So in the cascode, therefore the cascode transistor which is sitting on the top of the driving transistor is behaving like a shock absorber or a shield. So between the output node voltage variations to the, then that is earlier what I said. Oh, if the varies, if the drain voltage of the cascode of the driving transistor, if this varies, then VGS of that varies, and therefore current is also decreasing. Therefore we were crying, right. Now that whatever is there, that's being addressed now, right. To some extent at least that variation is being arrested. This is what is. It is not that this much of variation will not be there. It is acting like a shock absorber. Is it okay? Right. So this is what is a shielding property of the cascode. So once this is done, very quickly I will try to just now say something about the differential amplifier. Why you want to just now go for differential amplifier? Differential amplifier, the purpose, differential signaling and the other one is single end signaling. There is a difference here. So what is the differential signaling? What is the differential signal? Anyhow, before I'm just going, should I stop? Okay, I'll stop here.